Hello there, and welcome to this quiet place where time moves differently and science unfolds without rush. Tonight, we're stepping away from the familiar rhythm of the present and moving backward, far backward, into a version of Earth that existed long before human memory, before recorded history, before even the shape of the continents began to resemble the maps we know. We're travelling to a period roughly 350 million years ago, to a world that would feel both recognizable and profoundly strange if you could somehow stand there and breathe its air. This is the Carboniferous period, a span of deep time that lasted approximately 60 million years. It's a name you might have encountered in passing, perhaps in a textbook diagram or a museum display case filled with fossilized ferns. But few stop to consider what that world actually felt like, what it meant to exist in an atmosphere where oxygen didn't hover around 21% as it does now, but climbed steadily to 35%, fundamentally altering the physics of breathing, the behavior of fire, and the maximum size of the insects that flew through prehistoric forests. The air itself was different, not in some abstract academic way, but in a manner that dictated whether a dragonfly could grow to the size of a hawk, whether a forest fire would spread or sputter, whether glaciers would advance across tropical lowlands or retreat into memory. Oxygen, invisible and often taken for granted, became the master variable of an entire planetary system, regulating life and climate through mechanisms both elegant and paradoxical. This isn't a story of sudden catastrophe or dramatic extinction. It's quieter than that. It's the story of swamps that persisted for millions of years, of carbon slowly buried beneath stagnant water, of tectonic plates drifting imperceptibly across the globe until their final collision reshaped everything. It's about how a planet regulates itself when pushed to chemical extremes, and how those extremes, temporary as they were, left behind coal seams that would one day power the Industrial Revolution and giant fossilized insects that would captivate our imagination across the centuries. So settle in, let your thoughts slow to the pace of geological change, and allow yourself to drift into a world where the very composition of the atmosphere determined the boundary between possible and impossible. If you're listening from somewhere quiet tonight, I'm grateful you're here, and if this kind of deep time exploration resonates with you, a like or a subscription helps this signal reach others who might also find comfort in these long, unhurried journeys through Earth's history. No pressure, just an invitation, like the gentle accumulation of organic matter in a carboniferous swamp, one layer at a time. We're going to move slowly through this story, letting each piece settle before moving to the next, because that's how the Carboniferous unfolded. Not in explosions, but in increments, in the patient arithmetic of photosynthesis and burial, fire and moisture, rise and inevitable decline. The air you're breathing right now is composed of roughly 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, and other gases making up the remainder. This composition feels permanent, stable, as though it's always been this way and always will be. But the atmosphere is not a constant. It's a variable, shaped by the interplay of geological processes, biological activity, and the slow churn of planetary chemistry across billions of years. Nitrogen, despite its dominance, is relatively inert in atmospheric terms. It doesn't react easily with other elements under normal conditions, which makes it a stable backdrop against which other gases fluctuate. Oxygen, by contrast, is intensely reactive. It combusts with organic matter, rusts iron, enables complex metabolism in animals, and fuels wildfires. Its concentration in the atmosphere is therefore not a given, but an outcome, determined by the balance between production and consumption, between photosynthesis and decay, between burial and oxidation. The modern 21% oxygen level represents a kind of equilibrium, one that has remained relatively stable for the past few million years. But this equilibrium is recent in geological terms. If you could plot atmospheric oxygen across the last 600 million years, you would see a graph of dramatic peaks and valleys, periods where oxygen surged upward or plummeted downward in response to shifts in the global carbon cycle, the extent of plant life, the configuration of continents, and the prevalence of anoxic ocean basins. The most famous atmospheric transformation is the Great Oxidation Event, which occurred roughly 2.5 billion years ago. Before this event, Earth's atmosphere contained virtually no free oxygen. The planet was anoxic, its surface chemistry dominated by methane, hydrogen sulfide, and other reduced gases. The emergence of photosynthetic cyanobacteria gradually introduced oxygen into the environment, fundamentally altering the chemistry of the oceans, the composition of minerals, and the evolutionary trajectory of life itself. This was a transformation that unfolded over hundreds of millions of years, a slow poisoning of anaerobic organisms, and a simultaneous opening of ecological space for oxygen-dependent life forms. But the Great Oxidation Event, as profound as it was, did not immediately produce the oxygen-rich atmosphere we experience today. Oxygen levels rose, then stabilized at lower concentrations for much of Earth's middle history. It wasn't until the rise of vascular land plants, roughly 450 million years ago, that atmospheric oxygen began its climb toward the levels that would define the Paleozoic era. The Paleozoic, the era of ancient life, spans the last 550 million years of Earth history. It encompasses the Cambrian explosion of animal diversity, the colonization of land by plants and arthropods, the rise of fish and amphibians, and eventually the dominance of early reptiles. Within this long span, oxygen levels fluctuated significantly, responding to changes in the extent of forests, the rate of organic carbon burial, and the intensity of weathering processes that regulate atmospheric carbon dioxide. The highest oxygen concentration in the entire Phanerozoic eon, the eon of visible life that includes the Paleozoic, Mesozoic, and Cenozoic eras, occurred during the Carboniferous period. This was not the first time oxygen had been present in the atmosphere, nor was it a sudden spike. It was instead the culmination of geological and biological processes that had been building across tens of millions of years, a slow crescendo driven by the unique conditions of a specific moment in Earth's tectonic and climatic history. The Carboniferous oxygen maximum is estimated to have reached concentrations between 30 and 35%, a 14-point increase over current levels. In terms of partial pressure, this meant that the effective concentration of oxygen available for diffusion into biological tissues was roughly 50% higher than it is today. This difference, seemingly modest in percentage terms, had profound consequences for the physiology of respiration, the dynamics of combustion, and the structure of terrestrial ecosystems. Oxygen at these concentrations alters the fundamental physics of diffusion. For organisms that rely on passive oxygen transport, such as insects, the increased partial pressure means that oxygen can travel farther into tissues without requiring active circulation. For fire, higher oxygen levels lower the ignition threshold and increase the intensity and speed of combustion. For climate, the processes that produce high oxygen, specifically the burial of organic carbon, simultaneously remove carbon dioxide from the atmosphere, driving global cooling and glaciation. The Carboniferous period, therefore, was not simply a time of high oxygen. It was a time of interlocking atmospheric extremes. High oxygen paired with exceptionally low carbon dioxide, a combination that created a world both hyperoxic and frigid, a planet where giant insects flew through humid forests, while glaciers advanced across portions of the southern supercontinent. This duality, this coexistence of chemical opposites, defines the Carboniferous and distinguishes it from every other period in Earth's history. Understanding the Carboniferous requires understanding that atmospheric composition is not merely a backdrop to life, but an active participant, a force that shapes evolution, ecology, and climate with the same power as volcanic eruptions or meteor impacts, but operating on timescales measured in millions of years rather than days or centuries. The air is not neutral, it is reactive, dynamic, and in the Carboniferous, it was extreme. The Carboniferous period began approximately 358.86 million years ago and ended at 298.9 million years ago, spanning roughly 60 million years. To place this in context, the entire existence of the genus Homo, the lineage that includes modern humans, spans only about 2.5 million years. The Carboniferous alone lasted nearly 25 times longer than the entire history of our genus. This period sits within the Paleozoic era, positioned between the Devonian period that preceded it and the Permian period that followed. The Devonian had been a time of innovation. The first forests, the first seed plants, the emergence of tetrapods, four-limbed vertebrates that ventured onto land from freshwater environments. By the time the Carboniferous began, these experiments in terrestriality had matured into stable ecosystems, and the stage was set for the dominance of land plants on a scale never seen before or since. The Carboniferous is traditionally divided into two subperiods. The earlier portion, lasting from roughly 359 to 323 million years ago, is called the Mississippian in North American stratigraphy, named after rock formations exposed in the Mississippi River Valley. The later portion, from 323 to 299 million years ago, is called the Pennsylvanian, named after coal-bearing strata in Pennsylvania. In European and international stratigraphic schemes, these are often referred to as the Lower and Upper Carboniferous, but the two-part division reflects real differences in climate, geography, and the dominant forms of plant life. The Mississippian was characterized by relatively high sea levels and the widespread deposition of marine limestone. Continental interiors were often submerged beneath shallow seas, and the climate was generally warm and humid across much of the globe. Plant life on land included early seed ferns and the ancestors of the massive scale trees that would dominate the later Pennsylvanian forests, but these ecosystems were still developing, still experimenting with the architectural possibilities of life on land. The Pennsylvanian, by contrast, saw a shift toward lower sea levels, the expansion of vast coastal swamps, and the proliferation of dense, humid forests dominated by towering lycopsids and early tree ferns. This was the interval when coal formation reached its maximum, when organic carbon burial rates exceeded anything recorded before or after, and when atmospheric oxygen climbed to its peak. The Pennsylvanian is the heart of the Carboniferous oxygen maximum, the period when the chemical transformation of the atmosphere reached its most extreme expression. Geographically, the world of the Carboniferous was unrecognizable by modern standards. The continents were not arranged as they are today. North America, Europe, and parts of Asia were clustered together in a landmass called Laurasia, positioned near the equator where warm, humid conditions prevailed. To the south, the massive supercontinent Gondwana, comprising what would eventually become South America, Africa, India, Australia, and Antarctica, sprawled across the southern hemisphere, much of it situated over the South Pole. Between these two great land masses lay the Arctic Ocean, a body of water that was gradually closing as tectonic forces pushed the continents together. By the end of the Carboniferous and into the Permian, Laurasia and Gondwana would collide, forming the supercontinent Pangaea and fundamentally altering global climate, ocean circulation, and the distribution of terrestrial ecosystems. This slow tectonic convergence, spanning tens of millions of years, was not merely a rearrangement of geography. It was a driver of atmospheric chemistry, because the configuration of continents determined where swamps could form, where organic matter could be buried, and ultimately how much oxygen could accumulate in the air. The Carboniferous was also a time of glaciation, specifically the late Paleozoic Ice Age, which spanned from roughly 340 to 260 million years ago, overlapping significantly with the Carboniferous period itself. This glaciation was not a single continuous ice sheet, but a series of glacial interglacial cycles, periods when ice advanced and retreated across Gondwana in response to fluctuations in atmospheric carbon dioxide and changes in orbital parameters. The presence of ice during a time of high oxygen is not coincidental. The same processes that elevated oxygen levels, specifically the burial of organic carbon in anoxic swamps, simultaneously removed carbon dioxide from the atmosphere. Carbon dioxide is a greenhouse gas, one of the primary regulators of Earth's surface temperature. When vast amounts of it are sequestered underground in the form of coal, the greenhouse effect weakens and global temperatures drop. The Carboniferous was therefore a world of extremes: high oxygen and low carbon dioxide, warm equatorial swamps and polar glaciers, dense forests and frozen ice fields. Understanding the timing and context of the Carboniferous is essential because it situates this period not as an isolated anomaly, but as a logical outcome of specific geological and biological conditions. The oxygen maximum was not random. It was the product of plate tectonics creating the right geography, climate creating the right hydrology, and plant evolution creating the right type and quantity of organic matter. Remove any one of these factors, and the hyperoxic world would not have existed. Deep time is difficult to conceptualize. 60 million years is not a span that human intuition can grasp easily. It's longer than the entire age of mammals, longer than the recovery from the asteroid impact that ended the Cretaceous, longer than the entire Cenozoic era up to roughly 10 million years ago. Yet within that immense duration, processes unfolded slowly, incrementally, without drama or urgency. Forests grew, died, and were buried. Tectonic plates crept across the mantle at speeds measured in centimeters per year. Oxygen accumulated molecule by molecule, generation by generation, until the atmosphere reached a state that had never existed before and has never existed since. The Carboniferous sits in the middle distance of Earth's history, far enough back to be alien, close enough to be recognizable. Its fossils are abundant, its coal deposits are the foundation of modern industry, and its climate and atmospheric chemistry are well constrained by geochemical proxies. It is, in many ways, one of the best understood periods of deep time, and yet it remains profoundly strange, a reminder that the Earth we inhabit is not the only Earth that has ever existed. The Carboniferous period was defined not by a single atmospheric extreme, but by two opposing conditions that coexisted in a fragile, self-regulating balance. Atmospheric oxygen reached concentrations of 30 to 35%, while carbon dioxide levels plummeted to values comparable to, or even lower than, pre-industrial concentrations of roughly 280 parts per million. This pairing of high oxygen and low carbon dioxide created a planet that was simultaneously hyperoxic and glacial, a chemical state that has never been replicated in the subsequent 300 million years of Earth history. The relationship between these two gases is not coincidental. It is causal, driven by a fundamental aspect of the global carbon cycle. Oxygen is produced by photosynthesis, the process by which plants, algae, and cyanobacteria convert carbon dioxide and water into organic matter and molecular oxygen. Under normal circumstances, when organisms die and decompose, the reverse process occurs. Decomposition consumes oxygen and releases carbon dioxide, effectively reversing the chemical equation of photosynthesis and maintaining a rough atmospheric equilibrium. However, if organic matter is prevented from decomposing, if it is buried and isolated from oxygen before decay can occur, the carbon remains sequestered underground, while the oxygen produced during the organism's lifetime persists in the atmosphere. This process, known as organic carbon burial, is the only mechanism capable of producing a sustained increase in atmospheric oxygen on geological timescales. It is not enough for plants to simply exist and photosynthesize. They must also die and be buried in environments where decomposition is arrested, where the carbon they contain is locked away and prevented from re-entering the atmosphere. The Carboniferous was a period of extraordinarily high organic carbon burial rates, primarily due to the accumulation of plant debris in vast, waterlogged swamps. These swamps, dominated by towering leucopsids and early tree ferns, occupied low-lying tropical regions where water tables were high, drainage was poor, and the sedimentary basins were actively subsiding, creating space for organic matter to accumulate in thick layers. The resulting deposits, over millions of years, transformed into peat and eventually coal, representing the largest concentration of buried carbon in Earth's geological record. As carbon was removed from the active carbon cycle and locked underground, atmospheric carbon dioxide levels declined. This decline had immediate and profound climatic consequences. Carbon dioxide is a greenhouse gas, meaning it absorbs and re-radiates infrared radiation, trapping heat in the lower atmosphere and warming the planet's surface. When carbon dioxide concentrations drop, the greenhouse effect weakens and global temperatures decline. This is precisely what occurred during the Carboniferous, the late Paleozoic Ice Age, which began around 340 million years ago and persisted until approximately 260 million years ago, was a direct consequence of the carbon dioxide drawdown driven by coal swamp formation. Ice sheets advanced across portions of Gondwana, the southern supercontinent, covering regions that are now South America, Southern Africa, India, Australia, and Antarctica. Glacial deposits, including tillites and dropstones, provide clear evidence of ice coverage, while striations on bedrock surfaces record the movement of glaciers across the landscape. This glaciation was not uniform or continuous. It fluctuated in response to changes in orbital parameters, shifts in ocean circulation, and variations in the rate of organic carbon burial. During glacial maxima, ice sheets expanded and sea levels dropped, exposing continental shelves and altering the distribution of coastal swamps. During interglacial periods, ice retreated, sea levels rose, and swamp environments expanded once again. These cycles created a dynamic feedback loop. More swamps meant more carbon burial, which lowered carbon dioxide further, which intensified glaciation, which eventually disrupted the swamps themselves. The paradox of the Carboniferous is that it was both a time of lush, dense vegetation and a time of severe cold. The equatorial regions where the great coal swamps flourished were warm and humid, drenched in rain and bathed in sunlight, filtered through thick canopies of scale trees. But the higher latitudes, particularly in the southern hemisphere, were locked in ice, with temperatures well below freezing and ecosystems adapted to glacial conditions. The planet was divided, not by latitude alone, but by the chemical composition of its atmosphere, which allowed both extremes to exist simultaneously. This dual condition was inherently unstable, not in the sense of catastrophic collapse, but in the sense of delicate regulation. The system was self-limiting. If carbon burial rates increased too much, carbon dioxide would drop further, intensifying glaciation and potentially disrupting the very swamps responsible for the oxygen surge. If fire frequency increased due to high oxygen levels, vegetation cover would decline, reducing photosynthesis and carbon burial, which would allow carbon dioxide to rise again and oxygen to fall. The Carboniferous atmosphere was thus maintained by a set of interlocking feedbacks, a planetary thermostat that operated not on human timescales, but across millions of years. Understanding this duality requires abandoning the notion that atmospheric composition is a passive background condition. The air is not inert. It is reactive, dynamic, and deeply interconnected with the geology and biology of the planet. High oxygen did not exist in isolation. It was paired with low carbon dioxide because the same process, carbon burial, drove both conditions. The glaciers that covered Gondwana were not a separate phenomenon from the giant insects that flew through Pennsylvanian forests. They were two expressions of the same underlying chemistry, two sides of a single planetary equation. This interconnection is what makes the Carboniferous so instructive. It demonstrates that Earth's climate and atmospheric composition are not fixed, but are instead the outcomes of processes that can shift dramatically when the right conditions align. The modern atmosphere, with its 21% oxygen and rising carbon dioxide, is not inevitable. It is simply one possible state among many that the planet has occupied across its history. The Carboniferous represents another state, an extreme endpoint reached through a unique convergence of tectonic geography, plant evolution, and hydrological conditions that created the perfect environment for massive carbon sequestration. The age of dual extremes was temporary. It could not persist indefinitely because the geological forces that enabled it were themselves in motion, driven by the relentless drift of tectonic plates toward the assembly of Pangaea. But for 60 million years, the Earth existed in this strange, hyperoxic glacial state, a world that challenges our intuitions about how planets regulate themselves and reminds us that stability, when it occurs, is often the result of dynamic equilibria rather than static permanence. The name Carboniferous derives directly from the Latin words for carbon and bearing, a reference to the immense coal deposits that characterize this period. Coal is not merely an incidental feature of Carboniferous geology. It is the defining signature, the physical evidence of a planetary process that operated at a scale and intensity unmatched anywhere else in the geological record. The coal seams that underlie portions of North America, Europe, and Asia are the compressed, carbonized remains of ancient forests, preserved in strata that can reach dozens of meters in thickness and extend across hundreds of kilometers. Coal formation requires specific conditions. It begins with the accumulation of plant debris in environments where decomposition is inhibited. Typically, this occurs in wetlands, swamps, marshes, and floodplains, where water tables are high and organic matter is submerged beneath stagnant, oxygen-poor water. In these anoxic conditions, the bacteria and fungi that normally break down dead plant material cannot function efficiently, and the organic matter instead accumulates as peat, a dense, fibrous layer of partially decayed vegetation. Over time, as sediment is deposited on top of the peat, the weight of overlying material compresses it, squeezing out water and volatile compounds. The peat undergoes a transformation called coalification, a process driven by heat and pressure that gradually converts the organic matter into progressively more carbon-rich forms. The stages of coalification proceed from peat to lignite, a soft brownish coal with relatively low carbon content, to subbituminous and bituminous coal, which are harder and contain higher concentrations of carbon, and finally to anthracite, the hardest and most carbon-rich form of coal, which forms only under conditions of intense heat and pressure, typically associated with mountain-building events. The Carboniferous coal deposits are primarily bituminous, indicating that they formed under moderate pressure and temperature conditions over millions of years. These deposits are found in specific geographical regions, reflecting the distribution of swamp environments during the Pennsylvanian subperiod. The most extensive coal fields are located in what are now the Appalachian region of the eastern United States, the Illinois basin of the central United States, and the coal basins of northern Europe, including England, Wales, Germany, and Poland. During the Carboniferous, these regions were positioned near the equator, within the tropical belt, where rainfall was abundant and temperatures were warm year-round. The equatorial location was critical. Tropical climates provide the high precipitation and consistent warmth necessary to support dense, fast-growing vegetation. The absence of seasonal freezing or prolonged dry periods allowed forests to remain productive throughout the year, continuously generating organic matter that would eventually be buried and preserved. The geographical distribution of Carboniferous coal is not random. It reflects the tectonic configuration of the late Paleozoic world. The continents that would eventually collide to form Pangaea were still separated by oceans, and the regions that would become North America and Europe were part of a landmass called Laurussia, positioned astride the equator. The collision of Laurussia with Gondwana was underway but not yet complete, and the resulting tectonic activity created subsiding basins, areas where the Earth's crust was slowly sinking and creating space for sediment and organic matter to accumulate. These subsiding basins were essential to the coal formation process. Without subsidence, the accumulation of organic matter would have been limited by the available space. As the crust sank, more room was created, allowing peat layers to grow thicker and thicker over millions of years. Subsidence also ensured that the organic material remained below the water table, preserving the anoxic conditions necessary to prevent decomposition. In regions where subsidence was slow or absent, coal formation was much less extensive, even if vegetation was abundant. The scale of organic carbon burial during the Carboniferous is staggering. Estimates suggest that the amount of carbon sequestered in Carboniferous coal deposits represents a significant fraction of the total carbon that has been buried over the entire Phanerozoic eon. This massive removal of carbon from the atmosphere and biosphere had direct consequences for atmospheric chemistry, driving the oxygen surge and the carbon dioxide collapse that defined the period. Coal is not just a fossil fuel. It is an archive of atmospheric history, a record of the unique conditions that allowed organic matter to accumulate and persist, rather than being recycled back into the atmosphere. Each coal seam represents millions of years of plant growth, death, and burial, compressed into a layer that can be meters thick. The vertical structure of coal deposits often reveals repeated cycles of accumulation and burial, reflecting the oscillating sea levels and changing hydrological conditions driven by glacial-interglacial cycles. The legacy of Carboniferous coal extends far beyond the geological past. These deposits became the foundation of the Industrial Revolution, providing the energy source that powered steam engines, factories, and eventually electrical power generation. The coal that fueled 19th and 20th century industrialization was formed during a 60 million year interval when the Earth's atmosphere and climate existed in a state of extreme disequilibrium, driven by the unique interplay of tectonic geography, plant evolution, and hydrological conditions that have never been replicated since. Understanding the geography of coal means understanding that the Carboniferous was not a time of uniform global conditions, but a time of specific, localized environments that happened to align in ways that maximized carbon burial. The equatorial swamps of La Russia were the engines of the oxygen maximum, the places where the slow, patient work of photosynthesis and burial gradually transformed the atmosphere. Without these swamps, the Carboniferous would have been a very different world, one where oxygen remained at lower levels, and the great ice sheets of Gondwana never formed. The forests of the Carboniferous did not resemble the forests of today. Walking through a modern, temperate or tropical forest, you encounter trees built from wood, their trunks composed of xylem and phloem, vascular tissues that transport water and nutrients, and provide rigid structural support. Carboniferous forests, by contrast, were dominated by plants that bore only superficial resemblance to modern trees, organisms whose architecture and reproductive strategies set them apart from anything alive today. The dominant flora were the arborescent lycopsids, commonly referred to as scale trees. These plants belong to the same lineage as modern club mosses, small herbaceous plants that grow close to the ground in moist shaded environments. But the Carboniferous lycopsids were not small. They were colossal, regularly reaching heights of 40 to 50 meters, equivalent to a 15-story building, with trunks that could measure up to 2 meters in diameter at the base. The most well-known genera are Lepidodendron and Sigillaria, both of which have left extensive fossil records due to their abundance and the durability of their tissues. Lepidodendron, often called the scale tree, had a distinctive bark pattern composed of diamond-shaped scars left behind when the tree shed its leaves. These scars covered the entire trunk in a regular repeating pattern, giving the bark a textured, almost geometric appearance. Sigillaria, by contrast, had vertically arranged leaf scars that ran in columns along the trunk, creating a ribbed or fluted texture. Despite their size, these trees did not contain significant amounts of true wood. The trunks of lycopsids were composed primarily of a thick, stiff outer bark layer that provided structural support. Beneath the bark was a relatively narrow ring of vascular tissue responsible for transporting water and nutrients, and at the center was a large pith cavity, a hollow or spongy core that reduced the overall weight of the tree. This construction was fundamentally different from that of modern trees, which rely on dense wood to support their height and resist wind stress. The reliance on bark for structural integrity had consequences. Lycopsid trunks were rigid but brittle, more prone to snapping under mechanical stress than the flexible wood-based trunks of modern trees. Fossil evidence suggests that Carboniferous forests were frequently damaged by storms, with broken trunks and fallen trees accumulating in the swampy substrate. This damage, rather than being a disadvantage, contributed to the coal-forming process by rapidly adding large quantities of organic debris to the anoxic sediments where it could be preserved. Lycopsids reproduced via spores rather than seeds. At the top of each tree, usually in a crown of narrow grass-like leaves, were reproductive structures called strobili, cone-like organs that produced and released spores. These spores were encased in protective coatings and could be dispersed by wind or water to colonize new areas. The spores were small, lightweight, and produced in enormous quantities, a reproductive strategy that favored rapid colonization of disturbed or newly available habitats. The life cycle of a lycopsid was relatively short for such a large organism. Estimates suggest that scale trees grew rapidly, reaching full height within a few decades, then reproduced once and died, a pattern similar to that of modern bamboo. This rapid growth and single reproductive event, known as semal parity, meant that Carboniferous forests were dynamic, constantly cycling through phases of growth, reproduction, death, and regeneration. The standing biomass at any given moment was therefore a mix of young, rapidly growing trees and older reproductive individuals nearing the end of their life cycle. In addition to lycopsids, Carboniferous forests included early tree ferns, seed ferns and horsetails, all of which contributed to the overall plant diversity and structural complexity of the ecosystem. Tree ferns, members of the group Maratiales, had trunks composed of tightly packed leaf bases and adventitious roots, providing support without the need for true wood. Seed ferns, despite their name, were not true ferns, but an extinct group of plants that reproduced via seeds enclosed in fleshy structures, an intermediate step between spore-based reproduction and the fully enclosed seeds of later gymnosperms. Horsetails, related to modern equisetum, grew to sizes much larger than their living relatives, with some species reaching heights of 10 to 15 meters. These plants had jointed stems and whorls of narrow leaves at each node, giving them a segmented, almost mechanical appearance. Like lycopsids, they reproduced via spores and thrived in wet, poorly drained environments. The overall structure of a Carboniferous forest was therefore layered and heterogeneous. The canopy was dominated by the towering lycopsids, their crowns forming a dense, light-blocking layer at 40 to 50 meters above the ground. Below the canopy, tree ferns and seed ferns occupied the mid-story, creating a second layer of foliage at 10 to 20 meters. The understory was filled with smaller ferns, horsetails and low-growing lycopsids, while the forest floor was a tangle of fallen trunks, decaying leaves and standing water. The density of vegetation in these forests was extreme. The warm, humid climate and abundant rainfall supported year-round growth, and the lack of herbivorous mammals, which had not yet evolved, meant that plant biomass accumulated faster than it could be consumed. The result was a landscape choked with vegetation, where light rarely penetrated to the forest floor, and the air was thick with moisture and the smell of decay. These forests were not stable climax ecosystems, but rather dynamic, disturbance-driven communities. Storms, floods, and natural senescence constantly created gaps in the canopy, and the rapid growth rates of lycopsids and tree ferns allowed these gaps to be filled within a few decades. The constant turnover of vegetation meant that large quantities of organic matter were always being added to the sedimentary environment, fueling the coal-forming process. The architecture of scale trees, with their reliance on bark rather than wood, their rapid growth and semal-parity, and their preference for waterlogged, poorly drained soils, was perfectly suited to the conditions of the Carboniferous. These plants were not evolutionary oddities or failed experiments. They were precisely adapted to their time and place, exploiting a set of environmental conditions that would never be replicated again. When those conditions changed, when the swamps dried and the climate shifted, the scale trees vanished, leaving behind only their fossilized trunks and the coal seams that bear witness to their dominance. Photosynthesis is a chemical process so fundamental to life on Earth that it's easy to take for granted. At its core, the mechanism is straightforward. Plants absorb light energy, typically from the sun, and use that energy to convert carbon dioxide and water into glucose and molecular oxygen. The glucose serves as fuel for the plant's metabolic processes, while the oxygen is released into the atmosphere as a byproduct. This process, repeated trillions upon trillions of times across billions of individual organisms over millions of years, is what maintains the oxygen-rich atmosphere that complex animal life depends upon. The chemical equation for photosynthesis can be written simply: 6 molecules of carbon dioxide plus 6 molecules of water, in the presence of light energy, produce 1 molecule of glucose and 6 molecules of oxygen. But this simplified equation masks an enormously complex series of biochemical reactions occurring within specialized structures called chloroplasts, particularly within membrane systems called thylakoids, where light-dependent reactions take place. During the Carboniferous, photosynthesis operated under the same biochemical principles as it does today. The lycopsids, tree ferns, and other dominant plants possessed chlorophyll and other photosynthetic pigments that captured light energy and initiated the electron transport chains necessary for converting carbon dioxide into organic compounds. The rate of photosynthesis was determined by several factors: the intensity and duration of sunlight, the availability of carbon dioxide in the atmosphere, the availability of water and nutrients in the soil, and the temperature of the environment. The Carboniferous forests occupied equatorial regions where sunlight was abundant throughout the year. Unlike higher latitudes, where seasonal variations in day length and solar angle create distinct growing seasons, the tropics maintain relatively constant light conditions. This meant that photosynthesis could proceed year-round, without the dormancy periods that characterize temperate and boreal forests. The result was continuous carbon dioxide uptake and oxygen production, a relentless biochemical pump operating without interruption across millions of years. The atmospheric carbon dioxide concentration during the early Carboniferous was higher than pre-industrial levels, possibly reaching 400 to 600 parts per million. This elevated concentration provided abundant substrate for photosynthesis, allowing plants to grow rapidly and accumulate biomass efficiently. As the period progressed and carbon burial accelerated, carbon dioxide levels began to decline, eventually reaching values comparable to or even lower than the pre-industrial baseline of roughly 280 parts per million. This declining carbon dioxide concentration should theoretically have limited photosynthesis, as carbon dioxide is one of the essential reactants. However, the effect was partially offset by the increase in plant biomass. As forests expanded and became denser, the total photosynthetic surface area increased, compensating for the reduced carbon dioxide availability. Additionally, the high humidity and abundant rainfall of the equatorial swamps ensured that water, another essential photosynthetic reactant, was never limiting. The oxygen produced by Carboniferous photosynthesis did not immediately accumulate in the atmosphere. Under normal circumstances, most of the oxygen released during a plant's lifetime is consumed when that plant dies and decomposes. Decomposition is essentially the reverse of photosynthesis. Microorganisms break down organic compounds, consuming oxygen and releasing carbon dioxide. This cycle, when balanced, maintains atmospheric oxygen at relatively stable levels, because production and consumption rates are approximately equal. What made the Carboniferous different was not an increase in the rate of photosynthesis per se, but a dramatic decrease in the rate of decomposition. The key factor was the physical environment in which the plants grew and died. The vast swamps of the Pennsylvanian subperiod were characterized by standing water, poor drainage, and low oxygen availability in the sediments. When a lycopsid fell, or when leaves and branches accumulated on the forest floor, they quickly became submerged in stagnant water where oxygen concentrations were extremely low or absent entirely. In anoxic conditions, the aerobic bacteria and fungi that normally decompose plant material cannot function. Their metabolic processes require oxygen, and without it, they become dormant or die. Some anaerobic microorganisms can decompose organic matter in the absence of oxygen, but they work much more slowly and less efficiently than their aerobic counterparts. The result is that organic matter in anoxic environments decomposes only partially, leaving behind substantial quantities of unoxidized carbon. This incomplete decomposition was the critical step. Each generation of plants that grew, photosynthesized, died, and was buried in anoxic swamp sediments represented a net transfer of carbon from the atmosphere to the geological reservoir. The carbon dioxide that had been removed from the air during photosynthesis remained locked in the organic debris, while the oxygen that had been released remained in the atmosphere. Over time, as layer upon layer of plant material accumulated and was preserved, atmospheric oxygen concentrations climbed steadily upward. The scale of this process is difficult to comprehend. A single coal seam, perhaps 10 meters thick, represents millions of years of plant growth and accumulation. The original thickness of organic material was much greater, perhaps 30 to 50 meters, which was then compressed by the weight of overlying sediment into the dense carbon-rich coal we extract today. Each meter of coal contains the compressed remains of countless individual plants, each of which spent decades photosynthesizing and releasing oxygen before dying and contributing its carbon to the growing deposit. The cumulative effect across the 60 million year span of the Carboniferous was a transfer of billions of tons of carbon from the atmosphere into underground coal deposits. This removal of carbon, combined with the retention of oxygen, fundamentally altered atmospheric chemistry. The oxygen concentration rose from an estimated 25% at the beginning of the period to a peak of 30 to 35% during the late Pennsylvanian, an increase unprecedented in the geological record. Photosynthesis, therefore, was not simply a metabolic process occurring within individual plants. It was a planetary-scale engine, a biogeochemical pump that operated across millions of square kilometers of swamp forest, cycling carbon and oxygen between the atmosphere and the biosphere at rates sufficient to transform the composition of the air itself. The engine was powered by sunlight, fueled by carbon dioxide and water, and regulated by the hydrological conditions that determined whether organic matter would decompose or be preserved. This engine did not operate in isolation. It was part of a larger Earth system that included ocean chemistry, weathering processes, volcanic outgassing, and tectonic plate movements, all of which influenced atmospheric composition in various ways. But during the Carboniferous, the photosynthesis burial engine dominated, overwhelming other processes and driving the atmosphere toward an oxygen-rich, carbon dioxide-poor state that had never existed before and would never exist again. The patient, repetitive work of photosynthesis, occurring in countless chloroplasts within countless leaves across countless generations of plants, was the fundamental driver of the Carboniferous oxygen maximum. It was not a sudden event or a catastrophic shift, but a gradual accumulation, the result of millions of years during which production consistently exceeded consumption, and the balance tipped decisively toward the preservation of organic carbon and the liberation of atmospheric oxygen. The distinction between photosynthesis and oxygen accumulation is subtle but essential. Photosynthesis produces oxygen, but it does not by itself cause oxygen to accumulate in the atmosphere over geological time. For oxygen to build up, something must prevent the reverse process, decomposition, from consuming the oxygen that photosynthesis has produced. That something is burial, the physical isolation of organic matter from oxygen before decomposition can occur. Decomposition is the biological breakdown of organic material by bacteria, fungi, and other microorganisms. It is a necessary and ubiquitous process, essential for recycling nutrients and returning carbon to the atmosphere where it can be used again by photosynthetic organisms. In most environments, decomposition proceeds relatively quickly. A fallen tree in a temperate forest, for example, will lose most of its mass within a few decades as fungi colonize the wood, insects burrow through it, and bacteria break down the remaining cellulose and lignin. The process of decomposition is fundamentally oxidative. Aerobic decomposers consume oxygen while breaking down organic compounds, releasing carbon dioxide, water, and heat. This is why compost heaps generate warmth. The metabolic activity of microorganisms oxidizing organic matter releases energy. From an atmospheric perspective, decomposition reverses photosynthesis. The carbon that was removed from the air during the plant's lifetime is returned as carbon dioxide, and the oxygen that was released is consumed. The net effect in a balanced system is zero change in atmospheric composition. For oxygen to accumulate, this balance must be broken. Specifically, organic carbon must be sequestered, locked away in a form that prevents decomposition. This can occur in several ways. One is through rapid burial by sediment, which isolates organic matter from oxygen and halts aerobic decomposition. Another is through chemical preservation, where organic compounds are transformed into forms that resist microbial breakdown. A third, and the most important during the Carboniferous, is through submersion in anoxic water, where the absence of dissolved oxygen prevents aerobic decomposers from functioning. The Carboniferous swamps provided ideal conditions for anoxic burial. The dominant plants grew in low-lying, poorly drained basins where water tables were at or above the soil surface. Rainfall was abundant, often exceeding evaporation, which meant that water constantly saturated the soil and accumulated on the surface. The topography was flat, with minimal slope, so water moved slowly or not at all, creating vast expanses of standing water that became stagnant over time. Stagnant water quickly becomes anoxic. Oxygen dissolves in water, but only to a limited extent, and once the dissolved oxygen is consumed by decomposers and other organisms, it is not readily replenished unless the water is mixed with oxygenated surface water or exposed to the atmosphere. In the Carboniferous swamps, the thick canopy of vegetation shaded the water surface, reducing photosynthesis by aquatic plants and algae that might otherwise have produced oxygen. The water column was often stratified, with denser, oxygen-poor water trapped at depth unable to mix with the surface layers. When a lycopsid fell, or when leaves, branches and spores accumulated on the swamp floor, they sank into this anoxic water. The lack of oxygen meant that aerobic bacteria and fungi, which are the most efficient decomposers, could not survive. Some anaerobic bacteria could still function, but their metabolic processes are much slower and less complete. They tend to break down simple sugars and starches first, leaving behind more resistant compounds like cellulose, lignin, and waxes. Over time, this partially decomposed organic matter accumulated as peat, a dense, fibrous material composed primarily of plant remains in various stages of decay. Peat formation is the first step in coal formation. In modern environments, peatlands are found in cool, wet regions like northern bogs and tropical swamps, but the scale of Carboniferous peat accumulation far exceeded anything observed today. Peat layers in the Pennsylvanian subperiod could reach thicknesses of tens of meters, representing continuous accumulation over millions of years. The preservation of organic matter in anoxic conditions is not perfect. Some decomposition still occurs, and some carbon is released as methane, a byproduct of anaerobic metabolism. Methane is a potent greenhouse gas, and its release from Carboniferous swamps may have provided a minor counterbalance to the cooling effect of carbon dioxide drawdown. However, the overall rate of decomposition in anoxic environments is far lower than in oxygenated environments, meaning that the majority of organic carbon remains sequestered rather than being returned to the atmosphere. The physical mechanism of burial was aided by tectonic subsidence. The basins where the swamps formed were gradually sinking due to tectonic forces associated with the assembly of Pangaea. As the crust subsided, more space was created for sediment and organic matter to accumulate. Periodic influxes of sediment from rivers or coastal floods would bury the peat layers, adding weight and isolating them further from the atmosphere. Over millions of years, this burial process transformed peat into coal through a combination of heat, pressure, and chemical changes that expelled water and volatile compounds, leaving behind increasingly pure carbon. The key insight is that the Carboniferous oxygen maximum was not simply a product of abundant plant life. Abundant plant life existed in other periods without producing comparable oxygen levels. What made the Carboniferous unique was the combination of high productivity and efficient preservation. The swamps produced enormous quantities of biomass, and the anoxic, waterlogged conditions ensured that most of that biomass was buried rather than decomposed. This mechanism explains why oxygen levels did not continue to rise indefinitely. The system was self-limiting. For organic matter to be preserved, the swamps had to remain wet. But as carbon dioxide levels fell and global temperatures dropped, the climate began to shift. Glaciation intensified, sea levels fluctuated, and the hydrological conditions that maintained the swamps became less stable. Additionally, as we will see later, the assembly of Pangaea disrupted the tropical rainfall patterns that sustained the swamps, introducing seasonal aridity that dried the peat and exposed it to oxygen once again. The critical step then was not photosynthesis itself, but the prevention of decomposition through anoxic burial. This step transformed the Carboniferous forests from a carbon-neutral ecosystem, where production and consumption balanced, into a carbon sink, where production consistently exceeded consumption and the excess carbon was removed from the active carbon cycle. The oxygen produced by photosynthesis, no longer consumed by decomposition, accumulated in the atmosphere, driving oxygen concentrations upward over tens of millions of years until the system reached its maximum and the conditions that sustained it began to unravel. For much of the 20th century, a compelling explanation for the extraordinary coal accumulation of the Carboniferous was the so-called evolutionary lag hypothesis. This hypothesis posited that the fungi and bacteria capable of decomposing lignin, the complex polymer that provides structural rigidity to wood and bark, had not yet evolved during the Carboniferous. Without lignin-degrading organisms, the argument went, the massive trunks and branches of scale trees and other plants could not be broken down efficiently, leading to their preservation as peat and eventually coal. Lignin is indeed a challenging substance to decompose. It is a three-dimensional polymer composed of phenolic compounds linked by carbon-carbon and ether bonds, forming a rigid hydrophobic matrix that resists both chemical and biological breakdown. In modern ecosystems, lignin decomposition is carried out primarily by a group of fungi known as white rot fungi, which produce specialized enzymes, including lignin peroxidases and lacases, that can cleave the bonds within lignin and break it down into simpler compounds. The evolutionary lag hypothesis suggested that white rot fungi and their lignin-degrading enzymes did not evolve until late in the Carboniferous or early in the Permian, creating a window of millions of years during which woody plant material accumulated without being decomposed. This idea was attractive because it provided a simple, biologically driven explanation for an otherwise puzzling phenomenon. Why did coal formation peak during the Carboniferous and then decline in subsequent periods? However, more recent evidence has largely undermined this hypothesis. Molecular clock studies, which use genetic data to estimate the timing of evolutionary divergences, suggest that the ancestors of white rot fungi likely existed well before the Carboniferous, possibly as far back as the Devonian, or even earlier. Fossil evidence, though limited, also points to the presence of fungal decomposers in Carboniferous ecosystems. Fossilized wood from the period often shows signs of fungal colonization, including boreholes, decay patterns, and mineralized fungal hyphae. Additionally, lignin is not the only component of plant tissue, and many Carboniferous plants, including the dominant lycopsids, contained relatively low amounts of lignin compared to modern trees. The bark-based structure of scale trees, for example, was composed primarily of cellulose, suberin, and other compounds that are more easily decomposed than lignin. Yet these plants still formed the bulk of Carboniferous coal deposits, indicating that lignin content alone cannot explain the high preservation rates. If lignin-degrading organisms were present, why did organic matter accumulate so extensively during the Carboniferous? The answer lies not in the absence of decomposers, but in the physical and chemical conditions of the environment. Decomposition, regardless of the organisms involved, requires oxygen. Aerobic decomposition is far more efficient than anaerobic decomposition, capable of breaking down even resistant compounds, like lignin given sufficient time and oxygen availability. The Carboniferous swamps were oxygen poor. The waterlogged, stagnant conditions created an environment where dissolved oxygen in the water and pore spaces of the sediment was quickly consumed by what aerobic organisms were present and not readily replenished. Once oxygen was depleted, aerobic decomposers, including any lignin-degrading fungi, could not function. They require oxygen as a reactant in their enzymatic processes, and without it, their metabolic activity ceases. Anaerobic decomposers, which can function without oxygen, are far less efficient. They break down simpler compounds like sugars and starches relatively quickly, but they struggle with complex polymers like cellulose and lignin. The result is partial decomposition. The easily degradable components are consumed, while the more resistant components accumulate. Over time, this partially decomposed material is compressed and chemically altered, eventually forming peat and coal. The revised understanding, therefore, is that the Carboniferous coal accumulation was driven primarily by physical geography and hydrology, rather than by biological evolution. The key factors were the extensive low-lying swamp environments, the high water tables, the poor drainage, and the resulting anoxic conditions that inhibited decomposition. The presence or absence of lignin-degrading fungi was of secondary importance compared to the availability of oxygen. This interpretation is supported by the observation that coal continued to form, though at much lower rates in subsequent geological periods, when lignin-degrading fungi were certainly present. What changed after the Carboniferous was not the evolution of decomposers, but the loss of the extensive, waterlogged swamp environments that had characterized the Pennsylvanian subperiod. As the climate shifted toward aridity and the continents assembled into Pangaea, the swamps dried, oxygen penetrated the sediments, and decomposition resumed at normal rates. The debunking of the lignin lag hypothesis is a reminder that evolutionary explanations, while often compelling, must be tested against evidence and considered alongside other factors, particularly environmental and geological ones. The Carboniferous was not a time when biology paused, allowing organic matter to accumulate unchecked. It was a time when specific environmental conditions driven by tectonic and climatic forces, created a temporary window in which burial rates exceeded decomposition rates, regardless of the presence or absence of particular decomposer lineages. This distinction matters because it shifts our understanding of the Carboniferous oxygen, maximum from a biological anomaly to a geophysical phenomenon. The hyperoxic atmosphere was not the result of evolution failing to keep pace with plant diversification. It was the result of tectonic plate movements creating the right geography, climate patterns creating the right hydrology, and the interaction of these factors producing conditions that maximized carbon burial and minimized decomposition. The scale trees and other Carboniferous plants were not immune to decay. They were simply buried in environments where decay could not proceed efficiently. When conditions changed, when the swamps dried and oxygen returned, the accumulated organic matter became vulnerable to decomposition once again. But by that time, much of it had already been buried deep enough and compressed sufficiently to be locked away as coal, removed from the active carbon cycle for hundreds of millions of years, until humans would eventually extract it and return that ancient carbon to the atmosphere, reversing in centuries a process that took millions of years to complete. The Carboniferous oxygen maximum was not simply a biological event. It was a geophysical phenomenon, driven as much by the movement of tectonic plates and the configuration of continents as by the evolution and productivity of land plants. To understand why oxygen reached 35% during the Carboniferous, and not during other periods when forests were equally abundant, we must look at the unique tectonic and hydrological conditions that defined this interval of Earth history. Plate tectonics, the theory that Earth's lithosphere is divided into rigid plates that move across the underlying mantle, is the fundamental framework for understanding large-scale geological processes. During the Carboniferous, the major continents were in the process of colliding to form the supercontinent Pangaea. This was not a rapid collision, but a slow, inexorable convergence that played out over tens of millions of years, driven by the convective flow of material in the mantle beneath the plates. The collision of continents generates mountain ranges, a process known as orogenesis. During the Carboniferous, the collision of Laurussia, the combined landmass of North America and Europe with Gondwana, the southern supercontinent, produced the Appalachian Mountains in what is now the eastern United States and the Variscan mountain belt in Europe. These mountain-building events involved intense folding, faulting, and uplift of the crust, creating high topography along the collision zones. But mountain building is only one consequence of continental collision. Another, equally important, is the creation of foreland basins, low-lying areas adjacent to mountain ranges where the crust subsides under the weight of the mountains and the tectonic forces associated with the collision. These foreland basins become sedimentary repositories, places where rivers deposit sediment eroded from the mountains, and where organic matter can accumulate. During the Carboniferous, extensive foreland basins developed along the margins of the colliding continents. These basins were positioned near the equator, in the tropical belt where rainfall was abundant and temperatures were warm year-round. The combination of tropical climate and low-lying topography created ideal conditions for swamp formation. Water flowed from the highlands into the basins, but the flat terrain and poor drainage meant that water accumulated rather than flowing out to the ocean. The subsidence of these basins was critical. As the crust sank, it created accommodation space, room for sediment and organic matter to accumulate without being exposed to the atmosphere. In a non-subsiding environment, organic matter might accumulate for a time, but eventually the growing pile of debris would rise above the water table, exposing it to oxygen and allowing decomposition to resume. In a subsiding basin, however, the water table remains at or above the surface of the accumulating organic matter, maintaining the anoxic conditions necessary for preservation. The rate of subsidence varied across different basins and over time, but in many cases it was sufficient to allow peat layers to grow to thicknesses of tens of meters. The subsidence was driven by the weight of the overlying sediment and the tectonic forces associated with the ongoing continental collision, a combination of isostatic adjustment and dynamic subsidence linked to mantle flow patterns. The hydrological conditions within these basins were equally important. The equatorial position ensured high rainfall, often exceeding 2 to 3 meters per year. This rainfall fed rivers and streams that flowed into the basins, creating a constant influx of fresh water. However, because the basins were flat and poorly drained, the water did not flow rapidly through the system. Instead, it pooled, forming vast, shallow lakes and wetlands that covered thousands of square kilometers. The water in these swamps was not stagnant in the sense of being completely motionless, but it moved very slowly, with minimal mixing or aeration. The thick vegetation, including the canopy of scale trees and the dense understory of ferns and horsetails, shaded the water surface and reduced evaporation. The slow movement and high organic content of the water meant that dissolved oxygen was quickly consumed by aerobic organisms and not readily replenished, leading to anoxic conditions at depth and in the sediments. This anoxic environment was the key to carbon preservation. When plant material fell into the water, it sank into the anoxic zone, where aerobic decomposition could not occur. The material was partially broken down by anaerobic bacteria, but the process was slow and incomplete, leaving behind substantial quantities of organic carbon. As more plant material accumulated on top, the lower layers were compressed and buried, eventually transforming into peat. The tectonic configuration also influenced sea level, which in turn affected the extent of coastal swamps. During the Carboniferous, glaciation in Gondwana caused sea level to fluctuate in cycles, rising during interglacial periods when ice melted and falling during glacial maxima when water was locked up in ice sheets. These sea level changes caused the coastline to advance and retreat across the low-lying foreland basins, alternately flooding and exposing the swamp environments. When sea level rose, marine waters flooded the swamps, depositing layers of marine sediment on top of the peat. When sea level fell, the swamps expanded and more peat accumulated. This created a cyclical pattern of deposition known as cyclothems, repeated sequences of peat, marine limestone, shale and sandstone that reflect the oscillating environmental conditions. The cyclothemic pattern is characteristic of Carboniferous coal-bearing strata and provides clear evidence of the linkage between glaciation, sea level, and swamp dynamics. The tectonic assembly of Pangaea, therefore, was not a passive backdrop to the Carboniferous oxygen maximum, but an active driver. The collision of continents created the basins, the topography, and the subsidence necessary for swamp formation. The equatorial position of these basins ensured high productivity and abundant rainfall. The resulting hydrological conditions, characterized by stagnant anoxic water and high water tables, prevented decomposition and maximized carbon burial. Without this specific tectonic configuration, the Carboniferous oxygen maximum would not have occurred. Other periods had abundant plant life, even dense forests, but lacked the extensive waterlogged basins necessary for large-scale carbon burial. The late Devonian, for example, saw the first forests and significant expansion of land plants, but continental geography did not favor swamp formation, and oxygen levels remained moderate. Similarly, the Jurassic and Cretaceous periods had lush vegetation and high productivity, but the tectonic configuration and climate patterns did not create the same hydrological traps that characterized the Carboniferous. The lesson is that Earth system processes are interconnected. Atmospheric chemistry is not determined solely by biology, but by the interaction of biology with geology, climate, and hydrology. The oxygen factory of the Carboniferous was a product of plate tectonics, creating the right geography, climate creating the right rainfall patterns, and hydrology creating the right anoxic conditions. Remove any one of these factors, and the system collapses. The hyperoxic atmosphere was thus a contingent outcome, dependent on a specific and temporary alignment of geophysical conditions that would never be repeated. Respiration in insects and other terrestrial arthropods operates on principles fundamentally different from those in vertebrates. While vertebrates rely on lungs or gills to exchange gases with the environment, and use blood containing oxygen-binding proteins like hemoglobin to transport oxygen throughout the body, insects have evolved a completely different system based on direct gas exchange through a network of tubes called tracheae. The tracheal system begins at openings on the insect's body surface called spiracles. These spiracles, usually located along the sides of the thorax and abdomen, can be opened or closed to regulate gas exchange and minimize water loss. From each spiracle, a tracheal tube extends inward, branching repeatedly into smaller and smaller tubes called tracheoles, which eventually terminate at the cellular level, delivering oxygen directly to tissues and removing carbon dioxide. The movement of gases through this system occurs primarily via diffusion, the passive movement of molecules from areas of high concentration to areas of low concentration. When an insect's cells consume oxygen during metabolism, the oxygen concentration inside the tissues drops, creating a concentration gradient between the external atmosphere and the interior of the body. Oxygen molecules diffuse down this gradient, moving from the spiracles through the tracheal tubes and into the cells that need it. Diffusion is an effective mechanism for gas transport over short distances. At the microscopic scale, molecules move rapidly and randomly, and the concentration gradient ensures net movement in the desired direction. However, diffusion becomes increasingly inefficient as distance increases. The time required for a molecule to diffuse a given distance increases with the square of that distance, a relationship known as Fick's law of diffusion. This means that doubling the distance doesn't just double the time required, it quadruples it. For small insects, this is not a problem. A fruit fly, for example, is only a few millimeters long, and oxygen can diffuse from the spiracles to the deepest tissues within a fraction of a second. But as body size increases, the distances involved become much greater. A large beetle, several centimeters long, already pushes the limits of diffusion-based respiration. The oxygen must travel much farther to reach the core tissues, and the diffusion gradient must be steeper to maintain adequate oxygen delivery. This creates a fundamental constraint on insect body size. As an insect grows larger, its volume, and therefore its metabolic oxygen demand, increases with the cube of its linear dimensions. However, the ability to deliver oxygen via diffusion does not scale proportionally. The tracheal tubes must grow longer to reach deeper tissues, and longer tubes mean slower diffusion. To compensate, the insect must either increase the diameter of the tracheal tubes or increase the number of tubes, both of which require devoting a larger proportion of the body's internal volume to the respiratory system. This phenomenon is known as tracheal hypermetry. In larger insects, the tracheal system occupies an increasingly large fraction of the body volume, leaving less space for muscles, digestive organs, reproductive tissues, and other essential structures. Eventually, the insect reaches a size where the tracheal system would need to occupy so much space that there is insufficient room left for other organs, or where the diffusion distances become so great that oxygen delivery is inadequate to support metabolism. This represents a hard physiological limit on body size. At modern atmospheric oxygen levels of 21%, this limit restricts most insects to lengths of a few centimeters, with the largest extant species, such as certain stick insects and beetles, reaching lengths of 10 to 15 centimeters, but with relatively light bodies and specialized adaptations. Flying insects, which have particularly high metabolic demands due to the energy costs of flight, are generally even smaller, with the largest modern dragonflies having wingspans of around 12 to 13 centimeters. The physics of diffusion depends not just on distance but also on the concentration gradient, specifically the partial pressure of oxygen. Partial pressure is the contribution of a single gas to the total atmospheric pressure and is directly proportional to the concentration of that gas. At sea level, with oxygen comprising 21% of the atmosphere, the partial pressure of oxygen is approximately 0.21 atmospheres. If atmospheric oxygen concentration increases, the partial pressure of oxygen increases proportionally. This has a direct effect on the diffusion gradient. With more oxygen molecules present in the air at the spiracles, the concentration difference between the external atmosphere and the internal tissues becomes steeper, even if the internal oxygen concentration remains the same. A steeper gradient drives faster diffusion, allowing oxygen to travel farther into the body in the same amount of time. This is the key to understanding how the Carboniferous atmosphere enabled insect gigantism. At 35% oxygen, the partial pressure of oxygen was approximately 0.35 atmospheres, roughly 67% higher than today. This increased partial pressure meant that oxygen diffused more rapidly and more deeply into insect bodies, effectively extending the maximum diffusion distance without requiring proportionally larger tracheal tubes. In practical terms, an insect in a 35% oxygen atmosphere could maintain adequate oxygen delivery to tissues at body sizes that would be impossible in a 21% atmosphere. The diffusion constraint was relaxed, not eliminated, but sufficiently relaxed to permit body sizes several times larger than those possible today. The tracheal system still needed to scale with body size, and tracheal hypermetry still occurred, but the threshold at which the system became physiologically untenable was pushed to much larger sizes. This is not to say that high oxygen automatically produces giant insects. It removes a constraint, creating physiological capacity for larger sizes, but whether that capacity is realized depends on other factors, including ecological opportunities, evolutionary history, and selection pressures. However, without the high oxygen, the capacity simply does not exist. The diffusion constraint is a hard limit, a physical law that cannot be overcome by adaptation or evolutionary innovation. An insect breathing 21% oxygen cannot evolve to the size of a Carboniferous griffinfly because the physics of diffusion will not permit it. The Carboniferous atmosphere, therefore, was not just a backdrop to the evolution of giant arthropods. It was an enabling condition, a change in the fundamental parameters of respiration that opened evolutionary possibilities otherwise closed. The insects that exploited this opportunity, growing to sizes that would have been physiologically impossible in other time periods, were not anomalies or evolutionary mistakes. They were well-adapted organisms taking advantage of an atmospheric environment that permitted body sizes unattainable before or since. The increase in atmospheric oxygen from 21% to 35% during the Carboniferous represented a 14-point shift in concentration, but its physiological significance extended far beyond this numerical difference. What mattered for respiration was not simply the percentage of oxygen in the air, but the partial pressure, the effective concentration of oxygen molecules available to diffuse into tissues. At 35%, the partial pressure of oxygen was approximately 0.35 atmospheres, compared to 0.21 atmospheres today, an increase of roughly 67%. This increased partial pressure fundamentally altered the physics of gas exchange in insects. Diffusion, as described previously, depends on the concentration gradient between two regions. The steeper the gradient, the faster molecules move from high concentration to low concentration. In the context of insect respiration, the relevant gradient is between the oxygen-rich air at the spiracles and the oxygen-depleted environment inside the cells, where metabolism consumes oxygen continuously. When atmospheric oxygen concentration rises, the concentration at the starting point of diffusion, the spiracles, increases proportionally. If the metabolic demand of the tissues remains constant, meaning the cells consume oxygen at the same rate, the internal oxygen concentration stays roughly the same. The result is a steeper gradient, more oxygen outside, same amount inside, therefore a larger difference between the two. This steeper gradient drives faster diffusion, allowing oxygen molecules to move more quickly through the tracheal system. The implications for body size are profound. In a 21% oxygen atmosphere, oxygen can diffuse effectively over distances of perhaps a few centimeters before the gradient becomes too shallow to maintain adequate delivery. This limits insects to relatively small sizes. In a 35% oxygen atmosphere, the same diffusion mechanism can deliver oxygen over significantly longer distances because the enhanced gradient compensates for the increased path length. This can be visualized as an expansion of the viable respiratory radius. Each tracheal tube has an effective reach, a maximum distance over which it can deliver sufficient oxygen to support metabolism. When atmospheric oxygen increases, this radius expands, meaning that a single spiracle and its associated tracheal network can service a larger volume of tissue. An insect can therefore grow larger without needing to proportionally increase the number or diameter of its tracheal tubes, at least up to a new, higher threshold. The relationship is not perfectly linear. Doubling atmospheric oxygen does not double the maximum possible insect size, because body volume increases with the cube of linear dimensions while respiratory capacity scales differently. However, the relaxation of the diffusion constraint is substantial, Modelling studies suggest that the Carboniferous oxygen levels could have supported insects with body masses roughly 10 times greater than those possible at current oxygen levels and wingspans 5 times larger. This physiological release explains the observed fossil record. The largest known insect, the griffin fly Meganeuropsis permiana, had a wingspan estimated at 70 to 75 centimeters, approximately 5 times the wingspan of the largest modern dragonflies, which top out at around 13 to 15 centimeters. The body mass of Meganeuropsis has been estimated at around 150 grams, comparable to a small bird, whereas modern dragonflies rarely exceed a few grams. The increased oxygen availability did not just permit larger sizes, it also enabled more active lifestyles. Flight is one of the most metabolically demanding activities in the animal kingdom, requiring sustained high rates of oxygen consumption to power the muscles that beat the wings. Modern dragonflies are already among the most athletically capable insects, capable of hovering, rapid acceleration, and complex aerial maneuvers. The giant griffin flies of the Carboniferous would have required even higher metabolic rates to power their larger bodies and longer wings through the air. At 35% oxygen, this metabolic demand could be met. The enhanced diffusion gradient not only allowed oxygen to reach deeper into the body, but also allowed it to be delivered at higher rates, supporting the intense sustained muscle activity required for powered flight. The griffin flies were not sluggish, oversized versions of modern insects struggling to stay aloft. Fossil evidence suggests they were active, agile predators, capable of pursuing and capturing prey in flight. The physiology of oxygen delivery also influenced other aspects of arthropod biology. Larger body sizes generally correlate with longer lifespans, greater reproductive output, and increased resistance to environmental stresses, such as temperature fluctuations and desiccation. The giant arthropods of the Carboniferous likely benefited from these advantages, occupying ecological niches that would have been closed to smaller organisms. However, the physiological release was not unlimited. Even at 35% oxygen, diffusion still imposed constraints. There was still a maximum size beyond which the tracheal system would become too cumbersome, or diffusion would become inadequate. The largest Carboniferous arthropods approached this limit, but did not exceed it by orders of magnitude. The wingspans reached 75 centimeters, not 7 meters. The centipedes grew to 2 meters, not 20 meters. The oxygen increase expanded the envelope of possibility, but it did not eliminate all constraints. Additionally, high oxygen environments carry their own physiological risks. Oxygen is a highly reactive molecule, and excessive oxygen exposure can lead to the formation of reactive oxygen species, molecules that can damage cellular components including DNA, proteins, and lipids. Modern organisms have evolved antioxidant systems to protect against this oxidative stress, but there is a limit to how much protection these systems can provide. It is possible that the Carboniferous arthropods faced increased oxidative stress and required enhanced antioxidant defenses compared to modern insects. The trade-offs and benefits of high oxygen would have shaped the evolutionary trajectories of Carboniferous arthropods in ways that are difficult to reconstruct from fossils alone. What is clear is that the atmospheric chemistry provided an opportunity, a physiological release from constraints that had limited body size throughout earlier periods. The arthropods that exploited this opportunity, growing to unprecedented sizes and dominating terrestrial ecosystems as both predators and herbivores, were responding to a change in the fundamental parameters of their respiratory environment. When oxygen levels eventually declined during the Permian, this physiological capacity was withdrawn. The diffusion constraint returned with its full force, and the giant arthropods, no longer able to maintain adequate oxygen delivery to their tissues, disappeared from the fossil record. The window of opportunity opened by the hyperoxic atmosphere closed as the tectonic and climatic conditions that had sustained high oxygen levels unraveled, and the insects that had briefly achieved bird-like sizes returned to the centimeter-scale dimensions that characterize them today. The fossil record of the Carboniferous preserves a bestiary of arthropods that defy modern expectations of insect and arachnid body size. These organisms, preserved in fine-grained sediments and coal deposits, provide direct evidence of the physiological possibilities unlocked by the hyperoxic atmosphere. They were not marginal oddities or rare exceptions, but dominant members of their ecosystems, occupying roles as apex predators, herbivores, and scavengers across the swamp forests and adjacent environments. The most iconic of the Carboniferous giants were the griffinflies, members of the extinct order Protodonata. These were not true dragonflies, though they resembled them superficially, and are often referred to as giant dragonflies in popular literature. They shared a common ancestor with modern dragonflies and damselflies, but they diverged early in evolutionary history and developed unique characteristics that distinguished them from their living relatives. The genus Meganeura, known from fossils found in France, lived during the late Carboniferous, approximately 305 million years ago. Specimens of Meganeura moni show wingspans of up to 65 centimeters, with bodies that were robust and heavily muscled. The wings were elongated and narrow, with a dense network of veins that provided structural support and allowed for complex flight maneuvers. The head was dominated by large compound eyes, providing nearly panoramic vision suited to tracking fast-moving prey. Even larger than Meganeura was Meganeuropsis permiana, which lived slightly later, during the early Permian, around 290 million years ago. This species, known from fossils discovered in Oklahoma, had wingspans that reached 70 to 75 centimeters. The thorax was broad and powerful, housing the massive flight muscles necessary to propel such a large insect through the air. The legs were long and lined with spines, adaptations for capturing and holding prey in flight, a hunting strategy similar to that employed by modern dragonflies but scaled up to accommodate much larger victims. The diet of griffinflies is inferred from their anatomy and the structure of their mouthparts. They possess strong chewing mandibles capable of processing the hard exoskeletons of other arthropods. Likely prey included smaller insects, millipedes, and possibly even small vertebrates such as juvenile amphibians or early reptiles. The griffinflies were active hunters, relying on speed, agility, and excellent vision to locate and pursue prey across the open spaces above the swamp forests. Terrestrial predators were equally impressive. Arthropleura, a genus of giant millipede-like arthropods, reached lengths of up to 2.5 meters, making them the largest known terrestrial invertebrates of all time. Fossil trackways and body fossils from both North America and Europe document their presence in Carboniferous ecosystems. Despite their size, Arthropleura were likely herbivores or detritivores, feeding on plant material and decaying organic matter on the forest floor. The body of Arthropleura was segmented, with each segment bearing 2 pairs of legs, a characteristic of millipedes. The exoskeleton was thick and heavily armored, providing protection against predators, though at their size, adult Arthropleura may have had few natural enemies. The exact respiratory system of Arthropleura is not fully understood, but like other terrestrial arthropods, they likely relied on tracheal respiration, which would have required high atmospheric oxygen to support such a large body mass. Predatory arthropods extended beyond the insects. Fossil evidence documents centipedes, members of the class Chilopoda, that reached lengths of up to 2 meters. These animals were fast-moving carnivores equipped with venomous fangs, modified legs on the first body segment that injected toxins into prey. Modern centipedes are already formidable predators relative to their size, capable of subduing prey much larger than themselves through venom. The Carboniferous giants would have been apex predators in the leaf litter and undergrowth, hunting smaller arthropods, worms, and possibly small vertebrates. Scorpions, too, reached impressive sizes during the Carboniferous and Permian. Fossil specimens document individuals with body lengths approaching 1 meter, far exceeding the largest modern scorpions, which typically reach 10 to 20 centimeters. These scorpions retained the characteristic body plan of modern species, with a segmented tail ending in a venomous stinger and large pincers for grasping prey. They likely occupied similar ecological roles as ambush predators, waiting in concealment for prey to pass within striking distance. Spiders, though less well represented in the fossil record due to their fragile bodies, also participated in the Carboniferous size increase. Fossil spiders from this period show body lengths of several centimeters, and web-building species left behind trace fossils in the form of fossilized silk strands. The increased oxygen likely enabled larger body sizes in spiders as well, though they never approached the dimensions of the griffin flies or giant centipedes. The herbivorous insects of the Carboniferous also showed size increases, though they were generally smaller than the predators. Large cockroach-like insects, some with wingspans of up to 15 centimeters, were common in the fossil record. These insects likely fed on plant material, including the spores, seeds, and foliage of the dominant lycopsids and ferns. Their abundance suggests that they played an important role in nutrient cycling, consuming plant material and returning nutrients to the soil through their waste products. The presence of these giants throughout Carboniferous ecosystems indicates that the high oxygen atmosphere affected not just a few species, but entire communities. Size increases occurred across multiple arthropod lineages, including insects, myriapods, and arachnids, suggesting that the physiological release from the diffusion constraint was a general phenomenon rather than a lineage-specific adaptation. However, not all arthropods became giants. Many smaller species persisted, occupying ecological niches that did not favor large body size. Small insects continued to exist alongside their giant relatives, exploiting resources such as pollen, fungal spores, and decaying plant matter that did not require or benefit from large body size. The Carboniferous ecosystems were thus characterized by a wide range of body sizes, from millimeter-scale mites to meter-scale centipedes, reflecting the diversity of ecological opportunities available. The catalogue of giants is incomplete. The fossil record, though rich, preserves only a fraction of the organisms that lived during the Carboniferous. Soft-bodied arthropods, those without heavily mineralized exoskeletons, are rarely fossilized, meaning that many groups are likely underrepresented or completely absent from our knowledge. The true diversity of Carboniferous arthropods was almost certainly greater than what the fossils reveal. What the fossils do reveal, however, is unambiguous. The Carboniferous was a time when arthropods reached body sizes unprecedented in Earth history, enabled by atmospheric oxygen concentrations that relaxed the fundamental constraints on diffusion-based respiration. These giants were not evolutionary experiments or failed lineages. They were successful, ecologically dominant organisms that thrived for tens of millions of years before the changing atmospheric and ecological conditions of the Permian closed the window on insect gigantism. The physiological capacity for gigantism, enabled by high atmospheric oxygen, was a necessary condition for the existence of giant arthropods, but it was not sufficient. Capacity does not automatically translate into reality. Evolution requires not just the ability to grow large, but also selective pressures that favor large body size, or at minimum, the absence of strong pressures against it. The Carboniferous provided both the physiological capacity and the ecological opportunity, creating a window in which large body sizes were not only possible but advantageous. Body size in animals is subject to a complex array of selective pressures. Larger size often confers advantages, greater physical strength, enhanced ability to capture or defend against prey and predators, improved thermoregulation due to lower surface area to volume ratios, and increased reproductive capacity. However, larger size also carries costs, higher metabolic demands, longer developmental times, greater vulnerability to environmental stresses such as food scarcity, and increased visibility to predators. In modern ecosystems, insects are kept small, not just by respiratory constraints but by ecological pressures. Chief among these is predation by vertebrates. Birds, bats, lizards, frogs, and small mammals consume vast quantities of insects, and their hunting strategies are finely tuned to detect and capture insect-sized prey. Insects have responded by evolving small sizes, cryptic coloration, rapid reproductive rates, and evasive behaviors. A large, slow-moving insect in a modern ecosystem is at a severe disadvantage, likely to be detected and consumed long before it can reproduce. The Carboniferous, however, was a time before the evolution of highly efficient insect predators. Birds did not yet exist. They would not evolve until the Jurassic, more than 150 million years later. Bats, the most effective aerial insect predators, would not appear until the Eocene, nearly 300 million years after the Carboniferous. The terrestrial vertebrates of the Carboniferous were primarily amphibians and early reptiles, groups that were still in the early stages of adapting to life on land. The amphibians of the Carboniferous included large, crocodile-like temnospondyls that lived in or near water, feeding primarily on fish and other aquatic prey. While some amphibians ventured onto land, they remained largely tied to aquatic environments for reproduction and were not specialized predators of terrestrial arthropods. The early reptiles, including the ancestors of modern reptiles and mammals, were generally small, with body lengths of 10 to 30 centimeters. These animals likely consumed insects, but their small size and relatively low metabolic rates meant they were not capable of exerting strong predation pressure on large, fast-moving arthropods. This absence of specialized vertebrate predators created an ecological vacuum, a set of niches that were available but unfilled. Large-bodied predators were scarce, and the primary predators in terrestrial ecosystems were arthropods themselves. The giant centipedes, scorpions, and griffinflies were the apex predators of their environments, occupying roles that would later be filled by reptiles, mammals, and birds. This situation persisted for tens of millions of years, allowing arthropods to diversify and exploit body sizes that would become untenable once vertebrate predators evolved greater efficiency. The competitive landscape also favored gigantism in certain contexts. Among predators, larger body size often confers an advantage in capturing prey and defending resources. The griffinflies, with their large wingspans and powerful flight muscles, could pursue and capture prey that smaller insects could not, and they could defend productive hunting territories against competitors. Similarly, the giant centipedes and scorpions could subdue larger prey items, accessing food resources unavailable to smaller predators. For herbivores, large size provides protection against predation and allows access to food resources that are out of reach for smaller animals. The giant millipede Arthropleura, for example, could feed on plant material high on tree trunks or on the tough, fibrous bark of lycopsids, resources that smaller herbivores might struggle to process. Its large size and armored exoskeleton also provided defense against the predatory arthropods that shared its environment. However, the ecological window for gigantism was not permanent. As the Carboniferous transitioned into the Permian, vertebrate evolution accelerated. Early reptiles diversified into a wide range of forms, including specialized insectivores with adaptations for capturing and processing arthropod prey. These reptiles were more agile, had higher metabolic rates, and possessed more sophisticated sensory systems than their Carboniferous predecessors, making them far more effective predators. By the Middle Permian, the fossil record shows a decline in the maximum size of arthropods. Griffinflies persisted into the early Permian but disappeared by the middle of the period. Giant centipedes and millipedes became rarer, and by the end of the Permian, terrestrial arthropods had returned to sizes much closer to those observed today. This decline coincided with the diversification of small to medium-sized reptiles that were well suited to hunting large arthropods. The reduction in atmospheric oxygen during the Permian, as carbon burial rates declined and the coal swamps dried, also contributed to the disappearance of the giants. The physiological capacity for large size was withdrawn as oxygen levels fell, reimposing the diffusion constraint that had limited insect size in earlier periods. The giant arthropods were thus caught in a double squeeze. Declining oxygen reduced their physiological capacity, while evolving vertebrate predators increased the ecological costs of large size. The ecological window, therefore, was a temporary alignment of conditions. High oxygen provided the capacity, absent vertebrate predation provided the opportunity, and the combination allowed arthropods to achieve sizes that were both physiologically possible and ecologically advantageous. Once either condition changed, the window closed. Even if atmospheric oxygen were to rise again to Carboniferous levels today, the ecological landscape has been permanently altered by the evolution of efficient vertebrate predators, and it is unlikely that giant arthropods would re-emerge. This history illustrates an important principle. Evolution is contingent. The traits that evolve and the body sizes that are achieved depend not just on intrinsic biological capabilities, but on the ecological context in which organisms exist. The Carboniferous giants were products of their time, shaped by atmospheric chemistry that no longer exists, and ecological opportunities that have been foreclosed by subsequent evolution. They were not inevitable outcomes of arthropod evolution, but contingent expressions of a unique set of circumstances that briefly aligned to permit body sizes unmatched before or since. Fire is one of the oldest and most powerful feedback mechanisms in the Earth system, a process that links atmospheric chemistry, climate, and the distribution of vegetation. The presence of fire requires three elements: fuel, an ignition source, and sufficient oxygen to sustain combustion. During the Carboniferous, all three elements were present in abundance, and the resulting fire regime played a critical role in regulating atmospheric oxygen and shaping the structure of terrestrial ecosystems. The geological record preserves direct evidence of fire extending back to the late Silurian, approximately 420 million years ago, shortly after the first vascular plants colonized land. This evidence comes in the form of charcoal, also known as fusane, the carbonized remains of plant material that has been partially combusted. Charcoal is highly resistant to decomposition and preserves well in sedimentary rocks, providing a reliable marker of past fire activity. Charcoal is formed when plant material burns in the presence of limited oxygen, a condition known as pyrolysis. In a typical wildfire, the outer portions of burning wood are exposed to abundant oxygen and combust completely, producing carbon dioxide and water vapor. The inner portions, however, are shielded from oxygen by the surrounding flames and char instead, forming a brittle carbon-rich residue. This charcoal falls to the ground during or after the fire and becomes incorporated into sediments, where it can be preserved for hundreds of millions of years. The abundance of charcoal in Carboniferous sediments indicates that fire was frequent and widespread. Charcoalified plant fragments are found throughout coal-bearing strata, often interbedded with layers of peat, suggesting that the swamp forests themselves experienced periodic burning despite their waterlogged conditions. The presence of charcoal from a wide variety of plant tissues, including wood, bark, leaves, and reproductive structures, indicates that fires affected all components of the vegetation. Fire frequency and intensity are strongly influenced by atmospheric oxygen concentration. At low oxygen levels, below approximately 15%, fires cannot spread through vegetation because the rate of combustion is too slow to generate sufficient heat to ignite adjacent fuel. At higher oxygen levels, fires ignite more easily, spread more rapidly, and burn at higher temperatures. The relationship is nonlinear. Small increases in oxygen concentration can produce large increases in fire behavior. At the current atmospheric oxygen level of 21%, wildfire is a common and ecologically important process in many ecosystems, particularly in regions with seasonal rainfall patterns that create alternating wet and dry periods. Fires ignite from lightning strikes, volcanic activity, or spontaneous combustion of accumulated organic material, and they spread through forests, grasslands, and shrublands, consuming biomass and releasing carbon dioxide back into the atmosphere. At 35% oxygen, the theoretical fire behavior becomes extreme. Modeling studies suggest that ignition thresholds would be dramatically lowered, meaning that even moist fuels that would not burn at current oxygen levels could sustain combustion. Fire spread rates would increase substantially, and flame temperatures would rise, producing more intense and destructive burns. Under some scenarios, fire return intervals, the average time between fires in a given location, could drop to just a few years, compared to decades or centuries in modern fire-prone ecosystems. If fires occurred this frequently, the consequences for vegetation would be severe. Trees and other plants require time to regenerate after fire, and if fires return before regeneration is complete, vegetation cover can decline progressively over time. Theoretical models suggested that at 35% oxygen, global vegetation cover might be reduced by approximately 20% compared to fire-free conditions, as repeated burning prevented forests from recovering fully between fire events. This presents a paradox. The Carboniferous coal swamps, which were the primary engines of oxygen production, consisted of dense, fuel-rich vegetation growing in environments with abundant ignition sources, including lightning strikes associated with tropical thunderstorms. If fire frequency and intensity were as extreme as theoretical models suggested, the swamps should have been repeatedly incinerated, halting the accumulation of organic matter and preventing the oxygen surge in the first place. Yet the geological record shows that the swamps persisted for tens of millions of years, producing massive coal deposits that required sustained accumulation of plant material. How could this be reconciled? The answer lies in understanding fire behavior not just as a function of oxygen concentration, but as a function of fuel moisture content. Fire requires not just oxygen and fuel, but fuel that is sufficiently dry to ignite and sustain combustion. Water has a high heat capacity, meaning it absorbs large amounts of energy before its temperature rises. Wet fuel must be dried before it can burn, and this drying process consumes energy that would otherwise contribute to combustion and fire spread. In environments with high fuel moisture, fires may ignite but fail to spread effectively. The flames consume dry surface material, but cannot generate sufficient heat to dry and ignite the wetter fuel beneath or adjacent to the fire front. As a result, the fire self-extinguishes after consuming only a small fraction of the available fuel. This is commonly observed in modern tropical rainforests, which experience high rainfall and maintain high humidity even during dry seasons. Lightning strikes may ignite individual trees, but the fires rarely spread beyond the immediate ignition point. The Carboniferous swamps were characterized by exactly this condition: high fuel moisture content due to standing water, high humidity, and frequent rainfall. The same waterlogged anoxic conditions that prevented decomposition and enabled coal formation also acted as a natural fire suppressant, limiting the spread and intensity of fires even in the presence of high atmospheric oxygen. Fires could and did ignite, as evidenced by the abundant charcoal in the fossil record, but they did not spread uncontrollably through the living forests. This interpretation is supported by experimental studies using modern plant materials burned under controlled conditions at elevated oxygen concentrations. These experiments show that while ignition probability increases with oxygen concentration, the ability of fires to spread through moist living vegetation does not increase proportionally. High moisture content can suppress fire spread even at oxygen concentrations as high as 30 to 35%, particularly in environments where the vegetation itself contains high water content. The Carboniferous fire regime, therefore, was characterized by high ignition frequency but limited fire intensity and spread. Fires occurred regularly, consuming dry surface litter, dead standing wood, and the drier portions of the canopy, but they rarely devastated large areas of living forest. This created a dynamic equilibrium. Oxygen production continued because the forest persisted, but oxygen accumulation was moderated by the steady, low-intensity combustion of accumulated organic material. Fire acted as a thermostat, preventing oxygen from rising to even higher concentrations while allowing it to remain elevated relative to earlier and later periods. This feedback mechanism was self-regulating. If oxygen levels rose too high, fire frequency would increase, consuming more vegetation and releasing more carbon dioxide, which would lower oxygen and raise carbon dioxide, eventually reducing fire frequency again. If oxygen levels fell, fire frequency would decrease, allowing more vegetation to accumulate and increasing carbon burial, which would raise oxygen levels once more. The system oscillated around an equilibrium point determined by the balance between photosynthesis, burial, and combustion. Understanding fire as a planetary feedback mechanism highlights the complexity of the Earth system. Atmospheric composition is not determined solely by biological or geological processes in isolation, but by the interactions among these processes, mediated by physical factors such as moisture, temperature, and the distribution of vegetation. The Carboniferous hyperoxia was sustained not by the absence of fire, but by the presence of water, which moderated fire and allowed the oxygen-producing swamps to persist in the face of an atmosphere that should theoretically have incinerated them. The coexistence of extreme atmospheric oxygen concentrations and vast fuel-rich swamp forests represents one of the most intriguing puzzles of Carboniferous Earth. Theoretical predictions based on combustion chemistry and fire behavior modeling suggested that the planet should have experienced catastrophic fire regimes that would have rendered the persistence of dense vegetation nearly impossible, yet the geological evidence tells a different story. Coal deposits meters thick, charcoalified plant remains indicating fire activity, and sedimentary structures consistent with long-lived, stable wetland environments. The paradox demanded resolution. Early models of Carboniferous fire dynamics relied heavily on laboratory experiments that measured ignition thresholds and flame spread rates under varying oxygen concentrations. These experiments, typically conducted on dried plant materials in controlled environments, demonstrated clear relationships. Higher oxygen concentrations lowered ignition temperatures, increased flame spread rates, and produced more complete combustion. Extrapolating these results to ecosystem scales suggested that at 35% oxygen, fires would ignite from even minor heat sources and spread rapidly through available fuel. One influential calculation estimated that fire return intervals in Carboniferous forests could have been as short as 1 to 5 years, meaning that any given location would experience fire almost continuously on geological timescales. Another modelling effort suggested that such frequent burning would reduce standing biomass by 20% or more, as vegetation would be repeatedly killed before reaching maturity and contributing to carbon accumulation. These predictions seemed incompatible with the existence of forests productive enough to generate the enormous coal deposits that define the period. The paradox became particularly acute when considering the swamp environments themselves. Modern wetlands and swamps are generally fire-resistant, precisely because of their high moisture content. However, the Carboniferous swamps were not uniformly wet. Seasonal variations in rainfall, driven by the megamonsoonal climate system developing as Pangaea assembled, would have created periods of lower water tables and drier surface conditions. During these dry periods, accumulated plant litter and standing deadwood could theoretically have dried sufficiently to burn, especially given the enhanced ignitability provided by high oxygen levels. Lightning provided an abundant ignition source. Tropical regions experience frequent thunderstorms, and the Carboniferous equatorial swamps would have been no exception. Lightning strikes to tall lycopsids would have been common, and each strike represented a potential fire ignition event. The question was not whether fires ignited, charcoal evidence confirms that they did, but whether these ignitions translated into landscape-scale conflagrations that consumed living vegetation and interrupted the carbon burial process. The resolution of the paradox required a more nuanced understanding of fire behavior, one that accounted for the full range of factors influencing combustion, not just oxygen concentration. Fuel moisture content emerged as the critical variable. Early modelling had often assumed that fuel moisture would equilibrate with ambient humidity on short timescales, meaning that during dry seasons, all fuel would become dry enough to burn. However, actual measurements of fuel moisture in modern wetland ecosystems revealed a more complex pattern. Living vegetation maintains high internal moisture content through active physiological processes, including water uptake from roots and regulation of transpiration through stomata. Even during dry periods when surface litter dries out, living leaves, stems, and trunks retain substantial water content, often 60 to 80% of their fresh weight. This water acts as a heat sink, absorbing energy during fire exposure and preventing temperatures from rising high enough to sustain combustion in living tissues. Experimental studies using fresh living plant materials under elevated oxygen conditions confirm this protective effect. While dried plant materials burned readily at 35% oxygen, fresh materials with moisture contents above 50% were much more resistant to ignition and flame spread. Fires could still ignite in dry surface litter and consume dead standing wood, but they struggled to transition into the living canopy, where fuel moisture remained high. This distinction between surface fires and crown fires is critical. Surface fires burn through litter, duff, and small woody debris on the forest floor, releasing heat and consuming fuel, but leaving most living vegetation intact. Crown fires, by contrast, spread through the canopy, killing trees and consuming the bulk of the forest's biomass. The high fuel moisture content of living Carboniferous vegetation would have favoured surface fires over crown fires, even at elevated oxygen concentrations. The waterlogged nature of the swamp substrates provided additional fire resistance. Standing water, even if only a few centimeters deep, creates a physical barrier to fire spread. Surface litter floating on water can burn, but the fire cannot spread downward into the saturated peat beneath or laterally across water-covered ground. The mosaic of wetter and drier microsites within the swamps would have created natural fire breaks, fragmenting potential fire spread and limiting the area affected by individual ignition events. Seasonal rainfall patterns also played a role. The megamonsoonal climate of the late Carboniferous produced distinct wet and dry seasons, but these were not uniformly dry. Rainfall during the dry season was reduced but not absent, and humidity remained high due to the extensive water surfaces and transpiration from vegetation. This persistent moisture reduced the duration and intensity of the fire season, the period when conditions were dry enough for fires to spread effectively. The revised understanding suggests that Carboniferous fire regimes were characterized by frequent ignition but limited spread. Lightning strikes ignited fires regularly, perhaps dozens or hundreds of times per year across a given swamp landscape. Most of these fires burned small areas, consuming surface litter and dead wood, before self-extinguishing when they encountered wetter conditions or living vegetation with high moisture content. Occasionally, during particularly dry intervals or in areas with lower water tables, fires could spread more extensively, but these events were the exception rather than the rule. This fire regime had important ecological consequences. The regular consumption of surface litter by small fires prevented the accumulation of deep, dry fuel layers that could support more intense burning. It maintained a patchwork of burned and unburned areas, creating habitat heterogeneity that supported diverse arthropod and vertebrate communities. It also returned some carbon to the atmosphere as carbon dioxide, acting as a partial brake on the oxygen surge, but not at rates sufficient to prevent the overall accumulation of oxygen to extreme levels. The paradox, therefore, is resolved not by eliminating fire, but by recognizing that fire behavior in the Carboniferous was moderated by moisture, just as it is in modern ecosystems. High oxygen increased the frequency of fire ignition and allowed fires to burn in conditions that would be too moist at current oxygen levels, but it did not overcome the fundamental physical barrier imposed by high fuel moisture content. The swamps persisted, the coal accumulated, and the oxygen rose, all in the presence of fire, because water acted as the ultimate regulator, permitting fire to exist without allowing it to become destructive enough to collapse the system. This resolution highlights the importance of moving beyond single-factor explanations. The Carboniferous atmosphere was not simply high oxygen, but a complex state characterized by high oxygen, low carbon dioxide, abundant moisture, frequent fire, and dense vegetation, all coexisting in a dynamic equilibrium maintained by feedbacks operating on timescales ranging from hours for individual fires to millions of years for tectonic and climatic shifts. Understanding this complexity is essential for understanding how the hyperoxic world could exist at all. Water is perhaps the most effective natural fire suppressant on Earth, and its role in the Carboniferous fire regime cannot be overstated. While oxygen concentration determined the potential for combustion, water determined whether that potential was realized. The same hydrological conditions that enabled massive carbon burial by preventing decomposition also prevented the landscape-scale fires that could have destroyed the vegetation producing the oxygen in the first place. The physics of water's fire-suppressing properties are straightforward but powerful. Water has an extraordinarily high specific heat capacity, meaning it requires substantial energy to raise its temperature. Specifically, it takes approximately 4.2 joules of energy to raise the temperature of 1 gram of water by 1 degree Celsius. This is roughly 4 times the heat capacity of dry wood and 5 times that of most soil materials. When fire encounters moist fuel, much of the heat energy released by combustion is absorbed by water in the fuel, raising its temperature rather than igniting adjacent material. Additionally, water undergoes a phase change at 100 degrees Celsius, transitioning from liquid to vapor. This phase change requires even more energy, approximately 2,260 joules per gram, a quantity known as the latent heat of vaporization. This means that before wet fuel can ignite, All the water it contains must first be heated to boiling and then evaporated, processes that consume enormous amounts of energy and effectively insulate the combustible material from the heat of nearby flames. In the context of the Carboniferous swamps, this meant that living vegetation with high internal moisture content was highly resistant to fire. A lycopsid trunk containing 60% water by weight would need to lose most of that water before the cellulose and other organic compounds could reach ignition temperature. During a fire event, the outer bark might char and dry surface materials might burn, but the living tissues beneath remained protected by their water content, preventing the fire from killing the tree or spreading through the canopy. The presence of standing water on the swamp floor provided even more direct fire suppression. Water bodies, even shallow ones, act as absolute barriers to surface fire spread. A fire burning through surface litter will extinguish immediately upon reaching water, as the flames cannot cross the gap, and the heat is dissipated into the water rather than preheating fuel on the far side. The Carboniferous swamps were characterized by complex microtopography, with hummocks of slightly elevated ground where trees grew, separated by depressions filled with standing water. This created a natural mosaic of flammable and non-flammable surfaces. When fires ignited, typically from lightning strikes to tall trees, they would spread across the drier hummocks, consuming leaf litter, fallen branches, and standing dead wood. But as the fire front approached the water-filled depressions, it would either stop entirely or jump across narrow gaps to the next dry area, leaving unburned islands of vegetation. The result was a patchy burn pattern, where individual fire events affected only a fraction of the landscape, perhaps 10 to 30% of the total area, rather than sweeping across entire regions as fires do in drier ecosystems. Humidity, the amount of water vapor in the air, also played a crucial role. High humidity reduces the rate at which fuel dries out and increases the moisture content at which fuel equilibrates with the atmosphere. In modern fire-prone ecosystems, fuel moisture content typically drops below 20% during the dry season, making vegetation highly flammable. In the humid Carboniferous swamps, even during drier periods, fuel moisture likely remained above 30 to 40% due to constant transpiration from vegetation and evaporation from water surfaces. The dense canopy of the lycopsid forests contributed to this humidity by shading the ground and reducing air circulation. Beneath the canopy, temperatures were moderated, wind speeds were low, and humidity remained persistently high, creating conditions analogous to a modern tropical rainforest understory. These conditions extended the protective effect of moisture beyond just the living vegetation to include the entire lower forest environment, making fire spread through the understory slow and difficult, even when surface fuels were technically dry enough to burn. Rainfall patterns reinforced the water barrier. The equatorial position of the Carboniferous swamps ensured frequent rainfall throughout the year, even during nominally drier seasons. Rainfall events directly extinguished active fires and re-wetted surface fuels, shortening the window during which fires could spread. The transition from wet to dry season was therefore not a binary switch from fireproof to fire-prone conditions, but a gradual modulation of fire probability and intensity, with fires becoming somewhat more frequent and slightly larger during drier periods, but never reaching the catastrophic scales predicted by oxygen-only models. The role of water extended beyond immediate fire suppression to influence the recovery and persistence of vegetation after fires. In ecosystems where fire is frequent and intense, plant communities evolve fire-adapted traits such as thick bark, resprouting ability, serotinous cones that open after fire, and rapid growth rates. The Carboniferous flora show limited evidence of such adaptations, suggesting that fire, while present, was not intense or frequent enough to drive strong selective pressure for fire resistance. This observation supports the interpretation that fires were primarily low-intensity surface burns rather than stand-replacing crown fires. The lycopsids, with their relatively thin bark-based trunks and lack of extensive woody tissue, would have been poorly equipped to survive high-intensity fires, yet they dominated the swamp forest for millions of years, indicating that the fire regime did not pose an existential threat to the dominant vegetation. The feedback between water and fire was ultimately self-stabilizing. The persistence of wet conditions allowed vegetation to accumulate, providing fuel for fires but also maintaining the moisture content that limited fire intensity. As long as the hydrological conditions that created the swamps remained stable, the fire regime remained moderate, and the carbon burial process continued. Water was not simply one factor among many. It was the critical regulator that allowed all other processes to function, the physical mechanism that resolved the apparent paradox of a hyperoxic, fuel-rich world that did not burn itself to ash. Modern analogues provide some insight. Tropical peatlands in Southeast Asia and the Amazon basin experience similar conditions: high productivity, waterlogged soils, and elevated fire risk during dry periods. Under normal conditions, these peatlands are fire-resistant due to high moisture content. However, when drainage or prolonged drought lowers water tables, they become extremely vulnerable to fire, and peat fires can burn underground for months, releasing enormous quantities of carbon. The Carboniferous swamps avoided this fate because the hydrological conditions remained stable across millions of years, maintained by the tectonic geography and tropical climate that created them in the first place. Understanding water as the primary fire suppressant in the Carboniferous reframes the relationship between oxygen and fire. Oxygen determined the baseline fire behavior, the rate at which fuel could combust under ideal conditions. Water determined whether those ideal conditions were ever achieved. In the constant interplay between these two forces, water maintained the upper hand, preserving the forests that produced the oxygen and creating the conditions that allowed the hyperoxic atmosphere to persist far longer than combustion chemistry alone would predict. The Carboniferous oxygen maximum was not a runaway process that spiraled towards some theoretical limit, nor was it a static condition maintained by external constraints. It was instead a dynamic equilibrium, a state reached when multiple feedback mechanisms balanced each other, creating a stable but not permanent configuration of atmospheric chemistry, climate, and biosphere. Understanding this equilibrium requires examining the feedbacks that both drove oxygen upward and limited its further accumulation. The primary positive feedback was the carbon burial cycle. Photosynthesis by swamp vegetation consumed atmospheric carbon dioxide and produced oxygen. When that vegetation died and was buried in anoxic sediments before decomposing, the carbon was sequestered underground while the oxygen remained in the atmosphere. This process, repeated continuously across millions of square kilometers of swamp forest and millions of years of time, drove oxygen concentrations steadily upward and carbon dioxide concentrations steadily downward. As oxygen accumulated, it triggered several negative feedbacks that limited further increases. The first was fire. Higher oxygen concentrations increased the frequency and intensity of fire, which consumed organic matter and released carbon dioxide back into the atmosphere. While water suppressed fire intensity, fire still occurred, and each fire event represented a partial reversal of the carbon burial process, consuming accumulated organic matter that would otherwise have been preserved. The relationship between oxygen and fire creates a thermostat-like mechanism. If oxygen rises above a certain threshold, fire frequency increases, consuming more vegetation and releasing more carbon dioxide, which reduces photosynthetic substrates and slows oxygen production. If oxygen falls below that threshold, fire frequency decreases, allowing more organic matter to accumulate and increasing the rate of carbon burial, which raises oxygen again. The system oscillates around an equilibrium point where carbon burial and fire consumption balance. The second negative feedback operated through climate. The removal of carbon dioxide from the atmosphere reduced the greenhouse effect, causing global temperatures to fall. This cooling intensified glaciation in the southern hemisphere, which in turn affected sea level. Lower sea levels exposed more continental shelf, potentially creating new land area for swamp formation, but they also disrupted existing coastal swamps by draining them or altering their hydrology. The glaciation feedback was complex, with both positive and negative effects on the carbon burial system. Lower carbon dioxide concentrations also directly affected photosynthesis. Carbon dioxide is a substrate for photosynthesis, and when its concentration falls below a certain level, the rate of photosynthesis declines. Modern plants begin to show carbon dioxide limitation, below approximately 150 to 200 parts per million. During the late Carboniferous, carbon dioxide may have approached these low levels, potentially reducing the productivity of the swamp forests and slowing the rate of oxygen production. However, this effect was partially offset by the high oxygen concentration itself, some photosynthetic inefficiencies, particularly photorespiration, a process where the enzyme rubisco catalyzes a reaction with oxygen instead of carbon dioxide, waste energy, and reduce net carbon fixation. High carbon dioxide and low oxygen favor efficient photosynthesis, while low carbon dioxide and high oxygen favor photorespiration. The Carboniferous atmosphere, with low carbon dioxide and high oxygen, was therefore somewhat hostile to photosynthetic efficiency, creating another limitation on further oxygen accumulation. A third negative feedback involved the physiology of decomposition. While anoxic conditions prevented most decomposition, the activity of anaerobic bacteria still released some methane and carbon dioxide from buried organic matter. Higher oxygen levels in the atmosphere could potentially increase oxygen penetration into shallow sediments, allowing aerobic decomposition to occur in zones that would otherwise have been anoxic. This effect would have been subtle, but over millions of years, even small changes in decomposition rates could significantly affect the net carbon burial rate. The tectonic and hydrological conditions that enabled the swamps were also subject to change, though on longer timescales. The assembly of Pangaea was an ongoing process, and as the continents converged, the configuration of ocean basins, the patterns of atmospheric circulation, and the distribution of rainfall all shifted. These changes eventually disrupted the tropical swamp environments, but during the peak of the Carboniferous oxygen maximum, they provided relatively stable conditions that sustained the carbon burial engine. The equilibrium reached during the late Carboniferous, with oxygen at 30 to 35% and carbon dioxide at very low levels, represented the point where these various feedbacks balanced. Oxygen production through carbon burial was matched by oxygen consumption through fire, and, to a lesser extent, weathering of exposed rocks and oxidation of reduced minerals. Carbon dioxide drawdown through burial was matched by carbon dioxide release through fire, volcanic outgassing, and respiration by animals and microorganisms. This equilibrium was maintained not by any single controlling factor, but by the collective action of multiple processes operating across different spatial and temporal scales. Fire operated on timescales of hours to years, regulating oxygen on seasonal to decadal timescales. Carbon burial operated on timescales of years to millennia, regulating oxygen on millennial to million-year timescales. Tectonic processes operated on timescales of millions to tens of millions of years, determining whether the hydrological conditions necessary for swamps could be maintained. The stability of this equilibrium should not be overstated. It was not a fixed point, but a band of possible states, with oxygen likely fluctuating by several percentage points over timescales of thousands to millions of years in response to variations in climate, sea level, and volcanic activity. These fluctuations are difficult to resolve in the geological record, but proxy data suggest that oxygen levels were not perfectly constant but varied around a mean value during the late Carboniferous. The equilibrium was also inherently vulnerable to disruption by changes in the boundary conditions. As long as the tropical swamps remained extensive and productive, and as long as the hydrological conditions favoured anoxic burial, the system could maintain high oxygen levels. But if either condition changed, if the swamps shrank or dried, or if decomposition rates increased, the equilibrium would shift and oxygen would begin to decline. This vulnerability distinguishes the Carboniferous oxygen maximum from more stable atmospheric states. The modern atmosphere, with oxygen at 21%, has persisted for many millions of years because it represents a less extreme configuration, one that is less dependent on specific, narrow environmental conditions. The Carboniferous atmosphere, by contrast, required a precise set of circumstances to exist at all, and when those circumstances changed, the extreme oxygen levels disappeared relatively quickly on geological timescales as the system relaxed toward a new equilibrium. The concept of self-regulation is important here. The Carboniferous Earth system did not have a goal or a target oxygen level. It was not trying to maintain equilibrium. Instead, the equilibrium emerged naturally from the interactions of physical, chemical, and biological processes, each responding to local conditions without knowledge of or concern for the global state. The fact that these processes produced a coherent, relatively stable atmospheric configuration for tens of millions of years is a testament to the power of feedback mechanisms in complex systems. Understanding the Carboniferous as a self-regulating equilibrium rather than a runaway or externally controlled process provides insight into how Earth systems respond to perturbations. The planet has experienced many atmospheric states across its history, from the anoxic conditions of the Archean to the hyperoxic conditions of the Carboniferous to the current state. Each represents a different equilibrium, stable within certain boundary conditions but vulnerable to shifts when those conditions change. The transitions between these states are driven not by catastrophic events, though such events can trigger transitions, but by the gradual evolution of the boundary conditions that determine where the equilibrium lies. The assembly of Pangaea was one of the most significant tectonic events in Earth's history, a process that fundamentally reorganized the geography of the planet and altered the circulation patterns of both the atmosphere and oceans. This reorganization had profound consequences for climate, particularly for the distribution of moisture, and it was this shift toward aridity that ultimately dismantled the hydrological conditions necessary for the Carboniferous swamps and ended the oxygen maximum. Pangaea was not a single, instantaneous event, but a prolonged process of continental collision that began in the Devonian, accelerated through the Carboniferous, and reached its maximum configuration in the Permian and Triassic. The assembly involved the collision of multiple continental blocks, including Laurussia in the north and Gondwana in the south, with smaller microcontinents and island arcs caught in between. These collisions produced extensive mountain ranges, including the Appalachians, the Urals, and the Variscan Belt, and sutured the continents together into a single massive landmass that stretched from pole to pole. The formation of a supercontinent has predictable effects on climate, effects that have been documented through geological evidence and reproduced in climate models. The first effect is the reduction of coastal area relative to continental interior. In a world with many smaller continents, most land is relatively close to the ocean, and maritime influences, including moisture-laden air masses, can penetrate deep into continental interiors. In a supercontinent, much of the land is far from any coastline, thousands of kilometers from the moderating influence of the ocean. This continental interior becomes arid by necessity. Moisture-bearing winds originating over the ocean lose their water content as they travel inland, dropping precipitation as rain or snow when forced to rise over mountains or when they encounter cooler air masses. By the time these winds reach the heart of a supercontinent, they have been wrung dry, and the interior experiences low precipitation and high evaporation, creating desert or semi-arid conditions. The second effect of supercontinent assembly is the alteration of ocean circulation patterns. With continents arranged into a single landmass, the ocean basins are reorganized into one or two large oceanic bodies rather than several smaller ones. These large oceans develop different circulation patterns than smaller basins, with implications for heat transport from equator to poles and for the distribution of moisture via atmospheric processes. The closure of ocean basins during continental collision also eliminates seaways that previously allowed ocean currents to circulate between different regions, further disrupting established circulation patterns. The third effect, particularly relevant to the Carboniferous and Permian, is the development of a mega-monsoonal circulation system. A monsoon is a seasonal reversal of wind direction caused by differential heating of land and ocean. During summer, land heats more rapidly than ocean, creating a thermal low pressure over the continent that draws moisture-laden air from the ocean, producing heavy rainfall. During winter, the pattern reverses, with high pressure over the cold continent driving dry air toward the ocean. In a supercontinent configuration, this monsoonal effect is amplified. The enormous landmass of Pangaea heated and cooled more intensely than smaller continents, producing stronger pressure gradients and more extreme seasonal wind reversals. The result was a mega-monsoon, a circulation system characterized by very wet summers and very dry winters, with the intensity of both extremes exceeding anything observed in modern monsoon regions. Evidence for this shift towards seasonality and aridity appears in the geological record of the late Carboniferous and Permian. Sedimentary indicators of aridity include evaporites, minerals such as halite and gypsum that form when water evaporates from lakes or shallow seas, concentrating dissolved salts to the point of precipitation. Evaporites are rare in the Mississippian and early Pennsylvanian, but become increasingly common in the late Pennsylvanian and Permian, indicating that arid conditions were expanding. Other indicators include red beds, sedimentary rocks coloured by iron oxide minerals that form when iron-bearing minerals oxidize in the presence of air. Red beds are characteristic of arid and semi-arid environments, where seasonal drying exposes sediments to atmospheric oxygen. They contrast with the grey and black sediments typical of anoxic swamp environments, and their increasing abundance in the late Pennsylvanian and Permian signals the transition from waterlogged to drier conditions. Fossil soils, known as paleosols, provide additional evidence. Paleosols that formed in the Mississippian and early Pennsylvanian show features consistent with constant waterlogging, including glaying, a blue-grey coloration caused by the reduction of iron in anoxic conditions. By the late Pennsylvanian and Permian, paleosols increasingly show features of seasonal wetting and drying, including carbonate nodules that form in semi-arid soils and vertical cracking patterns caused by seasonal desiccation. The distribution of plant fossils also reflects this climatic shift. The early Pennsylvanian is dominated by lycopside and tree fern fossils, plants that required constant moisture and poorly drained soils. By the late Pennsylvanian and into the Permian, these moisture-dependent plants decline in abundance and are replaced by seed ferns and early conifers, groups that possessed adaptations for surviving seasonal drought, including deeper root systems, waxy leaf coatings to reduce water loss, and more efficient water transport systems. This transition was not uniform across all regions. Some areas, particularly those that remained near coastlines or that received moisture from orographic effects, where mountains force air upward, cooling it and causing precipitation, retained humid conditions into the Permian. But the vast equatorial lowlands that had hosted the great coal swamps of the Pennsylvanian dried progressively, and the continuous expanses of waterlogged forest fragmented into isolated patches separated by seasonally dry uplands. The mechanism driving this aridification was the interaction between the assembling supercontinent and the global atmospheric circulation. As Pangaea took shape, the tropical regions where the Carboniferous swamps had flourished became increasingly interior to the landmass, far from oceanic moisture sources. The megamonsoonal circulation intensified, bringing heavy rainfall during summer, but leaving the landscape parched during winter. The overall result was a reduction in the duration and reliability of the wet periods that the swamps depended upon. The transition was gradual, unfolding over millions of years, but its effects were cumulative. As the water table dropped, even seasonally, the anoxic conditions in the sediments were disrupted. Oxygen penetrated into peat layers that had previously been sealed from the atmosphere, allowing aerobic decomposition to resume. The balance between carbon burial and decomposition shifted, with burial rates declining and decomposition rates increasing. The oxygen-producing engine of the Carboniferous began to slow, and atmospheric oxygen levels, which had remained high for tens of millions of years, began their long decline toward the lower values that would characterize the Permian and subsequent periods. The transition from the humid, stable swamp forests of the Pennsylvanian to the more seasonal, fragmented landscapes of the late Carboniferous was not a smooth, gradual process. Instead, it was punctuated by a distinct ecological event known as the Carboniferous Rainforest Collapse, or CRC, which occurred approximately 307 million years ago, near the boundary between the Pennsylvanian and the early Permian. This event represents a significant ecological reorganization, a moment when the continuous expanses of wetland forest fragmented into isolated patches, triggering extinctions among specialized wetland organisms and opening opportunities for groups adapted to drier conditions. The CRC is recognized primarily through changes in plant and animal fossil assemblages. Before the CRC, during the Middle Pennsylvanian, fossil deposits show a relatively uniform flora, dominated by lycopsids, tree ferns, and other moisture-dependent plants. These assemblages are found across a wide geographic range, from what is now North America to Europe, indicating that similar swamp forest ecosystems extended across much of the equatorial region of Pangaea. The vertebrate fauna associated with these forests included diverse assemblages of amphibians, particularly large temnospondyls, and smaller forms adapted to aquatic and semi-aquatic lifestyles. After the CRC, fossil assemblages show a marked change. Lycopsid diversity declined sharply, with many species disappearing entirely and the remaining species becoming restricted to smaller, more isolated habitats. Tree ferns persist, but with reduced diversity. The plant groups that expand are seed ferns and early conifers, taxa that possessed adaptations for tolerating seasonal drought and lower soil moisture. These plants had existed before the CRC, but were relatively uncommon. After the CRC, they become dominant in many regions. The vertebrate fauna also changed dramatically. Many amphibian lineages, particularly those specialized for life in permanent water bodies, declined or went extinct. The groups that diversified after the CRC were the amniotes, the clade that includes reptiles, birds, and mammals. Early amniotes possessed several key adaptations for life in drier environments, most notably the amniotic egg. A self-contained reproductive structure with a protective shell and internal membranes that allowed embryos to develop on land without requiring standing water for reproduction. The timing and geographic extent of the CRC suggest that it was driven by climatic change rather than by a single catastrophic event, such as an asteroid impact or massive volcanic eruption. The collapse was not instantaneous, but unfolded over a period of perhaps 1 to 2 million years, a relatively short interval in geological terms, but long enough to reflect a sustained shift in environmental conditions rather than a momentary perturbation. The most likely driver was the intensification of the megamonsoonal climate associated with the ongoing assembly of Pangaea. As the continents converged and the interior of Pangaea became more isolated from oceanic moisture sources, the seasonality of rainfall increased. The total annual precipitation may not have decreased dramatically, but its distribution shifted from relatively constant year-round rainfall to a pattern of intense summer monsoons followed by prolonged dry winters. This shift from ever-wet to seasonally dry conditions was lethal to the lycopsid-dominated swamp forests. Lycopsids required constant soil saturation and could not survive extended dry periods. Their shallow root systems, adapted to waterlogged soils, were ineffective at accessing deep groundwater during droughts. Their rapid growth strategy, which allowed them to dominate in stable, productive environments, became a liability when conditions became variable, as rapid growth requires consistent moisture availability. When the dry seasons began extending from a few weeks to several months, the lycopsid forests began to die back. The canopy thinned, allowing more light to reach the understory and changing the microclimate of the forest floor. Once continuous swamp habitats fragmented into isolated patches, separated by uplands that dried sufficiently during the winter months to no longer support wetland vegetation. These isolated patches could sustain small populations of wetland-dependent organisms, but they were vulnerable to local extinctions from random events such as fire or unusually severe droughts. The fragmentation of habitats is particularly devastating for species with low mobility and specialized habitat requirements. Many of the amphibians that declined during the transition from the humid, stable swamp forests of the Pennsylvanian to the more seasonal, fragmented landscapes of the late Carboniferous was not a smooth, gradual process. Instead, it was punctuated by a distinct ecological event known as the Carboniferous Rainforest Collapse, or CRC, which occurred approximately 307 million years ago, near the boundary between the Pennsylvanian and the early Permian. This event represents a significant ecological reorganization, a moment when the continuous expanses of wetland forest fragmented into isolated patches, triggering extinctions among specialized wetland organisms and opening opportunities for groups adapted to drier conditions. The CRC is recognized primarily through changes in plant and animal fossil assemblages. Before the CRC, during the Middle Pennsylvanian, fossil deposits show a relatively uniform flora, dominated by lycopsids, tree ferns, and other moisture-dependent plants. These assemblages are found across a wide geographic range, from what is now North America to Europe, indicating that similar swamp forest ecosystems extended across much of the equatorial region of Pangaea. The vertebrate fauna associated with these forests included diverse assemblages of amphibians, particularly large temnospondyls, and smaller forms adapted to aquatic and semi-aquatic lifestyles. After the CRC, fossil assemblages show a marked change. Lycopsid diversity declined sharply, with many species disappearing entirely and the remaining species becoming restricted to smaller, more isolated habitats. Tree ferns persist, but with reduced diversity. The plant groups that expand are seed ferns and early conifers, taxa that possessed adaptations for tolerating seasonal drought and lower soil moisture. These plants had existed before the CRC, but were relatively uncommon. After the CRC, they become dominant in many regions. The vertebrate fauna also changed dramatically. Many amphibian lineages, particularly those specialized for life in permanent water bodies, declined or went extinct. The groups that diversified after the CRC were the amniotes, the clade that includes reptiles, birds, and mammals. Early amniotes possessed several key adaptations for life in drier environments, most notably the amniotic egg, a self-contained reproductive structure with a protective shell and internal membranes that allowed embryos to develop on land without requiring standing water for reproduction. The timing and geographic extent of the CRC suggests that it was driven by climatic change rather than by a single catastrophic event, such as an asteroid impact or massive volcanic eruption. The collapse was not instantaneous, but unfolded over a period of perhaps 1 to 2 million years. The ultimate dismantling of the Carboniferous oxygen maximum was not caused by a single event or a sudden catastrophe. It was instead the result of a gradual, inexorable shift in the boundary conditions that had sustained high oxygen levels for tens of millions of years. The tectonic forces that had created the ideal geography for coal swamps, the foreland basins and coastal lowlands with poor drainage and high water tables, were the same forces that ultimately destroyed those conditions as the assembly of Pangaea progressed toward completion. The key mechanism was the progressive aridification of the tropical regions where the swamps had flourished. As Pangaea took its final form during the latest Carboniferous and early Permian, the interior of the supercontinent became increasingly isolated from oceanic moisture sources. The megamonsoonal circulation intensified, creating strong seasonal contrasts, and the overall climate shifted from humid and ever-wet to seasonally dry and, in many areas, semi-arid or arid. This shift was driven by the basic physics of atmospheric circulation over large land masses, and was therefore inevitable once the continents had converged sufficiently. The consequences for the swamp ecosystems were profound. The waterlogged anoxic conditions that had enabled carbon burial required constant moisture and high water tables. As rainfall became more seasonal and the duration of dry periods extended, water tables dropped. Even if the total annual precipitation remained relatively high, the concentration of rainfall into a few months followed by prolonged dry seasons meant that soils that had been permanently saturated now experienced seasonal drying. When soils dry, oxygen from the atmosphere diffuses into the pore spaces between sediment particles, replacing the water that had previously filled those spaces. This oxygen allows aerobic bacteria and fungi to colonize zones that had been anoxic and decomposition resumes. The organic matter that had accumulated in the sediments during wet periods, peat in various stages of transformation, becomes vulnerable to oxidation. Aerobic decomposers begin breaking down the partially decayed plant material, consuming oxygen and releasing carbon dioxide. This process represents a reversal of the carbon burial mechanism. Instead of removing carbon from the atmosphere and leaving oxygen behind, the system begins consuming atmospheric oxygen and returning stored carbon as carbon dioxide. The balance shifts from net carbon sequestration to net carbon release, and atmospheric oxygen, which had been climbing or holding steady at high levels, begins to decline. The rate of this decline was determined by the rate at which formerly anoxic sediments were exposed to oxygen, and the rate at which aerobic decomposition could process the accumulated organic matter. This was not a rapid process. Peat deposits could be many meters thick, and oxygen penetration into dense peat is slow, limited by diffusion, through narrow pore spaces. The decomposition of resistant compounds like lignin and other recalcitrant organic polymers proceeds slowly even under aerobic conditions. The decline in atmospheric oxygen therefore unfolded over millions of years, a long, gradual descent from the 35% peak of the late Pennsylvanian toward the lower values of the middle Permian. The decline was accelerated by other factors. As the swamps fragmented and their total area decreased, the rate of new carbon input through photosynthesis declined. Less plant material was being buried, while previously buried material was being exposed and oxidized. The net effect was a shift in the global carbon budget from a strong sink during the peak of the Carboniferous to a weaker sink, or even, in some regions and time periods, a source. Volcanic activity may also have played a role. The collision of continents that formed Pangaea was associated with extensive volcanic activity along the suture zones where the continents met. Volcanic eruptions release carbon dioxide directly into the atmosphere, and the rate of volcanic outgassing may have increased during the intense mountain-building episodes of the late Carboniferous and early Permian. This additional carbon dioxide input would have partially offset the effects of carbon burial, contributing to the rise in atmospheric carbon dioxide and the decline in oxygen. The changing ocean chemistry also contributed. The low atmospheric carbon dioxide of the Carboniferous had altered the chemistry of the oceans, reducing the concentration of dissolved carbon dioxide and affecting the carbonate system that regulates ocean pH and the ability of organisms to build shells and skeletons. As atmospheric carbon dioxide began to rise again, the oceans absorbed some of this gas, but the process also involved the release of previously stored carbon from ocean sediments, further contributing to the rise in atmospheric carbon dioxide. The decommissioning of the oxygen factory was thus not a single process, but a cascade of interconnected changes, all driven by the fundamental shift from wet to dry conditions as Pangaea assembled. The tectonic forces that had created the ideal conditions for carbon burial, the foreland basins and coastal plains of the colliding continents, were the same forces that eventually eliminated those conditions by creating a supercontinent interior too far from the ocean to remain humid. This sequence illustrates a fundamental principle of Earth system dynamics. The same forces that create extreme conditions often contain the seeds of those conditions' destruction. The assembly of Pangaea created the coal swamps by generating subsiding basins and positioning them in the humid tropics. But the assembly of Pangaea also destroyed the coal swamps by isolating the continental interior from moisture sources and introducing seasonal aridity. The oxygen maximum was thus a temporary state, sustained for a remarkable length of time, but always vulnerable to the continued evolution of the tectonic configuration that had enabled it. By the middle Permian, approximately 270 million years ago, atmospheric oxygen had declined to levels around 25%, still elevated compared to modern values but well below the Carboniferous peak. The giant arthropods, no longer supported by the high oxygen partial pressures that had enabled their gigantism, had disappeared or declined to smaller sizes. The coal swamps had been replaced by seasonally dry woodlands and, in many regions, true deserts. The planet had entered a new climatic and atmospheric regime, one that would persist, with modifications through the Permian and into the Triassic, until the opening of the Atlantic Ocean and the breakup of Pangaea initiated another major reorganization of Earth's climate system. The oxygen factory of the Carboniferous had been decommissioned, not by catastrophe, but by the slow, patient work of tectonic forces, shifting continents, altering climates, and reorganizing the hydrological systems that had made the extreme oxygen levels possible. The hyperoxic world had come to an end, and the atmosphere began its long, slow return toward the composition it maintains today.